Okay, yesterday we have worked out most of the stuff that I wanted to talk about at the large displacement setting. Just to recall briefly, the main source of nonlinearity is kinematics, where you actually no longer you can use infinitesimal strain measure, and you have to come up with the appropriate strain measure, and we have introduced quite a few, basically from deformation gradient and its various versions like a cofactor determinant, measuring the change of the infinitesimal vector, infinitesimal surface area, and then infinitesimal volume. And then we worked out something you can use in computation from the right stretch tensor, left stretch tensor, right and left Cauchy green tensor, green Lagrange strain, and so on and so forth. So all these different strain measures have associated stresses, and we have worked out also a number of these stresses that are featuring in the different, let's say, equation that we developed. For example, the first pillar Kirchhoff is the replacement of the true Cauchy stress in the strong form of the equilibrium equation, and the second pillar is the replacement of the natural replacement of the true Cauchy stress in the weak form. But I showed that actually you can work the other way around. You can use first pillar Kirchhoff stress in the weak form, and so on and so forth. Once you understand how to do this transformation, you can simply do it. Then, given such a diversity of strain measures and stresses, basically you have to ask yourself, how do I pick up the right constitutive model? And then I advocated the constitutive model, which is basically the one on Samenon Kirchhoff, which says that, at least that's what Sjarli told him, or called it, although I'm sure that neither Samenon or Kirchhoff ever suggested any material of this kind. It says you take Hooke's law connecting the most usual strain measure in many of these books, talking very little about large deformation. This will be green Lagrange strain and corresponding stress, which is second pillar Kirchhoff. And turns out such a constitutive model cannot really handle everything nicely. And in particular, if you have very large compressive strain, that gives a completely unreasonable conclusion that let's say, squishing some specimen, you need zero stress. Of course, this is a consequence of lack of convexity of this function with the corresponding, of the free energy function with respect to these strain measures. And then mathematician John Ball came up with the conclusion that the best way of building a constitutive model would be to make a strain energy function to be convex with respect to the deformation gradient, its cofactor, and its determinant, which are intrinsic measures of change of length, surface, and volume. Today we'll check a little bit more on that, in particular how to develop this constitutive model for large deformation setting, and in particular we will need to do something like a use of these principal stretches. So this reduces the three-dimensional problem to the handling principal values, and then a big advantage of that, you kind of separate the geometric nonlinearity with some kind of material nonlinearity. Then you can build your free energy in terms of these principal stretches. It becomes just a scalar potential in terms of scalars, and then you can kind of work it out just like it was let's say a simple one-dimensional setting, because you handle, let's say, one principal stretch at a time. And there's especially of interest, I hope to present that, when you have a large deformation plasticity, if you happen to choose a logarithmic strain, which is one of the possible choices conjugate to a Kirchhoff stress, then you can work out a very nice formulation of plasticity, which happens to be probably today the most advanced. I have it in the book in chapter 4. If you go all the way to the end of the chapter 4, basically that allows you to have a large elastic, large plastic deformation, and use what is called multiplicative decomposition of this deformation gradient into elastic and plastic part, which reduces to multiplicative decomposition of your principal stretches. And then you take a logarithm, and turning this logarithm of, let's say, elastic stretch into one deformation, the logarithm of plastic stretch another, you get additive decomposition just like in the small deformation setting. So this is roughly what I wanted to talk about today. So let me pick up where I actually stopped. That was but we came all the way to the different developments, and we came here to a different representation, like what is called the material versus a spatial description of large displacement. So recall that we had previously was a principal virtual work, where it's featuring an internal work of internal forces the second pure Kirchhoff, and the corresponding variation of the green Lagrange strain, which are providing with the scalar product the total internal work that you can put in solid body, integrating this over the domain omega occupied by this solid body. Working with external forces, it's either distributed force B or applied traction T, again, is given by the corresponding scalar product with the virtual displacement W. Here you know that the green Lagrange strain is a nonlinear functional displacement, in particular quadratic. And when you take a variation, you still have a virtual green Lagrange strain to be a linear function of this displacement. So together here, you're hiding like some kind of cubic dependency on a displacement. You use some Kirchhoff material, and basically, if you want to go with the isoparametric interpolation, this is one of the rare cases where the linearization and discretization could be interchanged, because isoparametric interpolation give you the value of the fields that you're trying to compute, either displacement or strain or stress, to be just a linear combination of the nodal values. Hence, you can then first linearize the problem and then discretize. So if I'm linearizing this weak form, I'm taking the value of the weak form, a particular value of displacement, and then directional derivative in the direction of the incremental displacement, which is noted now in U. And you recover basically the tangent stiffness. That one consists of two parts. There's one part which is associated with the variation of the real strain measure E, and you have a uppercase delta times E multiplied by the elasticity tensor, and all that scalar product with a lowercase delta times E, which is a virtual strain. And this will define the material part of your tangent stiffness. And also, since you had the virtual strain to be a linear function of the total deformation, so when you take variation, you can still recover something. So I use a symbol which is uppercase delta, lowercase delta times Z. This is old name. So, you know, in France, somebody is called Bergeon, somebody called Pierre, and somebody called Jean-Pierre. So let's say little delta times E would be Jean-Pierre, and whatever big delta times E would be either Jean-Pierre, and so on. And this one would be really like somebody, you have a Jean and Francois and Pierre, whatever you put the three names. It's not often, but it's still possible, let's say. So this is just a name for this object here, which is obtained by taking the variation. There's a equivalent sign missing here. So this will be like the virtual displacement gradient transpose times the incremental displacement plus incremental displacement gradient transpose times virtual displacement. So once you've been through this, you have your weak form, and then you want to build the corresponding element arrays. So typically you go to isoparametric element. Here I picture the four-node quadrilateral element, which is produced by isoparametric element here, by this parent element placed between -1 and +1. So every straight line in the xc eta coordinates is mapped into the straight line in the physical coordinate. And we discussed this already, that none of these internal angles should be larger than 108 degrees. Otherwise, you get into the trouble of representing this uniquely. The transformation from the coordinate side to x and back is no longer bijection, so you don't have 1 and 1 point here to correspond to 1 and 1 point in real physical space, and everything breaks down. Now, in large deformation, obviously, this is something that one has to worry about, because given that you have very large deformation and large displacement, even if you start with a nicely, let's say, form these quadrilateral elements where none of the internal angles is larger than 108 degrees, there's nothing to stop you given large space and then deformation that at a certain point you produce those. Typically, the way you know it is if you compute Jacobian, you will get Jacobian determinant of the Jacobian matrix to take a negative value. Then you know that something went wrong. So it's typically advisable when you have this computation to always have a check to compute the value of Jacobian and to make sure that Jacobian is positive, so that you know that this transformation is still valid and you have no problems related to this type of errors, you know, that could basically occur. So we put isoparametric interpolation representing the real geometry by introducing these bilinear shape functions that are, let's say, the same that we already use for four-node elements. And we do the same thing for our incremental displacement and also virtual displacement. The only difference is instead of the nodal coordinates xa multiplying the shape function to get position vector x, you're multiplying the same shape function with the nodal the real displacement to get your incremental displacement field. and then you're multiplying the nodal value of virtual displacement to get your virtual displacement field. Hence, given that you have isoparametric interpolation, it's very easy to recreate the deformed configuration. You simply take the same function used systematically for incremental displacement and the coordinates, and you sum up the value of the nodal value of coordinates and this displacement, and you multiply by the same shape functions, and you have your deformed configuration. Adding increment after increment and increment, you can follow each and every deformed configuration. So this is certainly an advantage that one can use in this computation. Now, if I want to compute strain, I have to go and recall how I actually compute the strain components. Here I picture this for 2D case. So there's a first Green-Lagrange strain, which is E11, which is obtained with the derivative of the, let's say this, the deformed configuration position vector with the x transpose times the same vector d phi at dx minus 1, and all that multiplied by 1/2. And then basically here you have the same thing, only with the derivative with respect to y. And for the shear strains, you have this derivative of phi with respect to x transpose times d phi dy, and plus d phi dy transpose d phi dx. So how to build this derivative with respect to x? Well, it's easy since you have phi. You simply take the shape function derivative with respect to x and y that you compute with your usual subroutine of computing derivative of the shape functions, and you multiply this again with the sum of the nodal coordinates and the corresponding displacement vectors. So you can fill in all these values here and obtain your strains. And of course, then you multiply with the corresponding value of the elasticity modulus, which is basically here, which is packed into the matrix, and you get corresponding value of stresses, which is packed into 3×1 vector as well. So basically, this is pictured here. Namely, since I have to have a packing of a tensor of let's say this Green-Lagrange deformation into the vector with 3 components, then the ordering of these 3 components of the second pure Kirchhoff stress tensor is already predetermined in a way that assures that the scalar product between those 2 tensors, Green-Lagrange strain and second pure Kirchhoff stress, is the same as the scalar product between these vectors. The vector E, where I pack these my strains, and the vector S, where I pack the components of the stress. This D is the same that you use in a small strain setting. As we said, if you accept the sum and non-Kirchhoff material, you simply copy your D to be lambda bar plus 2 mu lambda bar, whatever, lambda bar plus 2 mu and 2 mu. Well, lambda bar is either lambda, if you have plane strain case, or lambda 2 times lambda divided by lambda plus 2 mu, or something like that. It is for the plane stress. That should be the other way around, actually, here. Sorry about that. So basically, the geometric stiffness matrix, this is the term that we need at the end, could be expressed as a incremental displacement U multiplied by the matrix GAB, and then all this scalar product with the nodal values of the virtual displacement. And this matrix G is an identity matrix which has on the multiplied by some kind of coefficient. This coefficient could be computed as a S11 derivative of NA and B with respect to X, S22 derivative of NA and AB with respect to Y, and then S12 derivative of NA with respect to X and B with respect to Y, and then the other way around, NA with respect to Y and B with respect to X. And so when all said and done, you have your internal force vector and you have a tangent stiffness matrix with both material and geometric term. So this will be a typical element, and you can see nonlinearity arising because of the nonlinear dependence on the second pure Kirchhoff stress and the nodal displacement. In particular, this is a cubic function. And then linearizing, you have these 2 parts of your tangent stiffness. There's one part which is material, and the other one part is geometric. So this geometric part, you can see, depends on the stress. Hence, you can introduce the pre-stressing to give the stiffness to your structure, even if it's very slender. By pre-stressing, this is the typical feature of this large deformation. And I gave you this small homework to kind of understand how you actually do that. Now, if I understood how to do this in terms of the second pure Kirchhoff stress and the Green-Lagrange strain, I want to show that it's very easy to transform to any other, let's say, interpretation. And this is what we call the material form. Could also be replaced with something that we call spatial description of spatial form. Namely, we can appeal to the Kirchhoff stress. That one is product between the true or Cauchy stress and the Jacobian of the deformation gradient. And basically, given what is the connection between this true stress and the second Euler Kirchhoff, S is equal to F minus 1 times J sigma times F minus transpose. Obviously, if I multiply by F on the left-hand side and F transpose on the right-hand side, on this S, I'm going to obtain my tau in this way. So please recall now tau is a stress tensor which is acting in the deformed configuration contrary to the second Euler Kirchhoff stress, which is acting in the initial configuration, but it is parameterized with the coordinates in the initial configuration. So that's why you have to have all the time this motion reestablished in this phi, so you can establish connection between those two configurations. So I'm still taking Lagrangian formulation, but the object I'm using are not necessarily those that are sitting in the initial configuration. So this is just fine as long as I'm using coordinates in the initial configuration. The computation is just repackaging these objects and nothing else. So when I take a Kirchhoff stress, given that the second Euler Kirchhoff stress is conjugate to the Green-Lagrange strain, the much as I transform the second Euler Kirchhoff to get the Kirchhoff stress, I'm doing now inverse transformation to a Green-Lagrange strain to get corresponding strain. It turns out this strain could be written as a 1/2 identity minus F minus transpose F minus 1. F minus 1 times F transpose is equal to B. So this is actually B. You're right, Cauchy-Green, left Cauchy-Green deformation tensor, inverse. And so this type of product is often called as Almansi deformation, which is conjugated to this type of thing. So basically, I can then pack the formulation. Initially, it was written as a, let's say, if I have internal energy for some anarchic of material, I can write it as quadratic form in the Green-Lagrange strain to be 1/2 E times C times E. And then C times E is the second Euler Kirchhoff stress. So I can also write as 1/2 E dot S, the second Euler Kirchhoff stress. But then introducing this transformation that I just alluded to here for tau and here for Almansi stress, I can basically that this could also be written as 1/2 the Kirchhoff stress dotted with the Almansi stress strain. So basically, I can obtain that given this internal energy as the potential in terms of a Green-Lagrange strain, I can obtain corresponding Kirchhoff stress by computing the derivative of this with respect to the Green-Lagrange strain, and then multiplying on the right with F and the left, on the left, sorry, with F, on the right with F transpose to get corresponding value of my stress. Hence, the internal work, one way of writing it, I can do the second Euler Kirchhoff dotted with the variation of Green-Lagrange strain. But again, I go through this transformation that gives me the Kirchhoff stress, and that gives me what is known as a variation of the rate of deformation tensor, which I can write as F minus transpose nabla tensoria W plus W tensoria F minus transpose nabla. But recall that we had this yesterday, that the F minus transpose nabla is equal to nabla phi, when nabla phi takes the derivative with respect to the coordinates in the deformed configuration, and you compute it in this way. So then I can write this in a very simple format, which is given here. There is also this object. This is done for the variation. You can also do it for the rate form. If you're talking not about virtual work by virtual power method, some people prefer that, but at the end, it comes out to be the kind of, if not the same, very similar thing, because it's all about linearizing certain quantities. So virtual, that means very small, that means you can linearize. And also rate is also like a just instantaneous change in time. So again, you can linearize. So for example, if you're linearizing, you can get your rate of deformation tensor, introducing this velocity gradient to be F dot times F minus 1, and then taking the time derivative of your Green-Lagrange strain, given that this is 1/2 F transpose F minus 1, computed the time derivative, you get here F transpose F minus transpose times the time derivative of transpose times F, plus F transpose times F dot F minus 1 times F. So this is, you recognize your L velocity gradient, this is your L transpose, and hence you can write this to be F times 1/2 L transpose L plus F transpose. So this will be this type of transformation. You get your rate of deformation tensor. So linearization of this could be, again, working out from the case that we've done for the Green-Lagrange strain, and just doing corresponding transformation, always to recover the Kirchhoff stress on second Euler Kirchhoff stress. The key result is this one. And then we take the other one so you can complement and this computation not change the total value. you recover the results like this. Basically, here you have a material part of your tangent stiffness, which has a virtual rate of deformation tensor times d tau d epsilon plus incremental rate of deformation tensor. And here we have this increment of the virtual rate of deformation tensor times the value of the Kirchhoff stress to get the complete tangent stiffness. So if you now, basically, if you want to use that in the constitutive equation, that's actually where the question rate would come. In other words, if I have that tau is computed as a F times S second pure Kirchhoff times F transpose, I'm now computing the time derivative. So that becomes the derivative of the first one. This is F dot, and I insert F minus 1 times F, so I can keep my tau here. Then I take a derivative of the last one, and this would be again F transpose dot, but I insert F minus transpose and here transpose, so I can keep my tau here. So I recognize this is L transpose, and I finally at the term where I take the rate of S, so that becomes F S dot times F transpose. So if you take a rate format as opposed to variation for the second polar Kirchhoff stress, given that this is the object that is defined in terms of X and that is sitting in the initial configuration, you simply compute S dot and that's it. But if you compute the Kirchhoff stress, given that this is a function of the coordinates in the initial configuration, but it is sitting in the deformed configuration, the computation of the rate or time derivative is certainly more complicated. So what is S dot here, that has to be changed with the tau dot, but tau dot, the rate of the tau with respect to time is not the only one. You have to also add these terms which are minus L times tau and minus tau times L transpose. And this is called the rate of the Kirchhoff stress, which replacing that rate of the second pure Kirchhoff stress. So basically, the idea that goes into this is the fact that we have to take into account that these objects are not in the initial configuration. So when you take in the derivative, and this they are in the deformed configuration. So for every instant in time, this configuration is changing. So if you take in time derivative of something sitting in the deformed configuration, the typical action is you kind of take this, transform it back to the initial configuration. So that brings you some additional terms. Then you take derivative once you're in the initial configuration. And then basically, then you transform it again to the deformed configuration. This transformation, when you pull it back to the initial configuration, is called pullback. And then when you take the result and put it back into the deformed configuration, it's called push forward in the book of Mars and Hughes. So they have this terminology, you have to get used to it. But it's rather clear when you have to do this transformation, starting from the stuff that you already have in material description. In my mind, this could be worked out very easily, just like the packaging. So basically, you packed it one way, you have only S dot, but for some reason you prefer tau, and then you have to a little bit to work a little bit more. So what would be reason to prefer tau? Well, the final thing, I think, and that was the mistake, as I said, it was in a very famous paper by Teram and Wilson, where they did this updated Lagrangian formulation. They missed that constitutive model has to be changing when you're doing this, rather than the one from the total Lagrangian formulation, because you have this transformation from one to another. So basically here you have, let's say you had a second pure Kirchhoff, stress to be a linear function of the green Lagrange strain. So the SDE, recall it was just elasticity tensor. And so basically now if you want to get corresponding d tau d epsilon, well, you have to take this elasticity tensor and you have to transform this with the corresponding components of the deformation gradient to get this type of thing. Because that's the only that's the only correct way when you want to keep the same end result. And so this was something that people kind of missed initially when you're talking about large deformation. But again, if you have a point of view, these are just different pictures with the different objects that are more or less convenient. This could be, I guess fairly straightforward. Only takes a little bit more exercise and getting used to transforming this. But it's really the only big deal is about this scalar products. You know, when you take something and you have a whatever words that most convenient. Well, this one, for example, when you have something and you want to recover your tau, obviously here you put F, so you have to cancel this F with F minus 1, and you put F transpose, you have to cancel this F transpose with F minus transpose, and as simple as that. So then basically they kind of equilibrate to the same thing, and then you recognize what this is and what that is, and then you simply conclude these results. Of course, you have to have idea whether you're actually going to be able to correspondingly, let's say, insert these things and so on and so forth. So what's the big deal of taking this spatial description with the Kirchhoff stress? Well, the big deal is kind of sparsity of the tangent operator. So I go back to my four-node element, and this time around I want to Kirchhoff stress, not second pure Kirchhoff stress. So recall I had this representation of geometry by using the parent element and the bilinear shape function that I constructed in this element, multiplied by these nodal values. Then I take incremental displacement. I take the same shape functions multiplied by the nodal values of displacement. I take the virtual displacement with the nodal value of the virtual displacement. I take the shape function. So the deformed configuration is established simply by adding the nodal value of coordinates and the displacement multiplied by these same shape functions. And then I can actually go and compute derivatives with respect to the coordinates in the deformed configuration by featuring this deformation gradient that I compute by taking derivatives of this phi. And then I apply this to the computational derivative of the shape function with respect to x, the coordinates in the initial configuration. And so basically I get my corresponding derivatives of the coordinates in the deformed configuration. So I can simply enhance my computation of the shape function derivative with this type of computation with the deformation gradient. Once I've done that, what's the big deal? Well, the big deal would be that when you have a virtual strain or when you have an incremental strain, the strain displacement operator B this time around has a very sparse structure. In fact, it has the same structure like in the small deformation setting. Only the difference is that these derivatives are computed not with the coordinates in the initial configuration, but with respect to the coordinates in the deformed configuration. And that's as simple as that. So basically, if you go to this incremental formulation, you have your incremental strain, which is again the same sparse matrix B times the incremental displacement nodal values. And then you can have a packing of these strains into three components. You can have a corresponding packing of the Kirchhoff stress into the three components. You have to compute your corresponding elastic modulus by going through this corresponding transformation that we alluded to. If you want to stick with the seminar Kirchhoff material, or you want to postulate some other material, doesn't really matter. And when all is said and done, you have your internal force vector with the Kirchhoff stresses, and then you have two parts of your tangent stiffness, the material and geometric part. And this time around, geometric part is computed from the Kirchhoff stresses rather than second pure Kirchhoff stresses. And these time derivatives, this space derivative with respect to the coordinates in the deformed configuration, where the coordinates in the deformed configuration obviously are computed by the deformation gradient and the derivatives with respect to the coordinates in the initial configuration. So this is all this packing that you have in detail in the book, and you can look into that. So I didn't really want to go step by step because there are many symbols, but at the end it's just like 2 or 3 observations that is like keeping the packaging always the same, or the end result always the same, and then you kind of work on this particular component you want to have, and not to change the other guys, you have to put it in equilibrate. So in conclusion of this, as I said, that we had represented the whole idea of what is the large deformation doing, and I try to do it in the simplest possible way using the fixed Cartesian coordinate system, so you avoid all this complexity of many presentations with the curvilinear coordinates of manifolds and stuff like that. So I first define a number of these strain measures, and then I show that all these strain measures should then have to be accompanied with the corresponding stresses, and then some of the stresses take prominent roles because they are replacing the true Cauchy stress. In the strong form, this is the first Euler-Kirchhoff, and then in the weak form, the second Euler-Kirchhoff. And then basically constitute the model is quite tricky to obtain. So if you take the simplest case with connecting the Hooke's law, a second Euler-Kirchhoff stress and Lagrange differential strain, you are in trouble because large compressive stresses are definitely not computed correctly. Then at the end, I showed you today the difference between spatial and material description. And that's about it, what I wanted to say here. So let me now take the story of a large deformation and try to see how we can build the constitutive model by taking into account the approach of the principal directions. So what I want to talk about today is again very quickly recall what is the elastic behavior in large deformation, some anarchical material, just to recall it, and then we can go into the correct, let's say, construction of these elastic deformation by appealing to a principal axis formalism at large deformation. And then I'll show how to extend the same type of formalism to plasticity. So this is quite interesting if you're working on this type of thing, and hopefully it could demystify many of these things. So first, I revisit my some anarchical material, which has a linear connection between Green Lagrange strain and the second pure critical stress. That is just elasticity tensor that I need. So in 1D setting, this was reminds that 1 over lambda sigma equal to C times du dx was 1/2 du dx squared. Obviously, this is already kind of strange measure, because for the positive value for tension, du dx and du dx squared will be going in the same direction, but for the negative value for compression, du dx and du dx squared are not the same sign. This one negative, so be positive. So even then, it's kind of you're not measuring, but the compression and tension the same way. Yet, if you ignore that, you just go down to a small strain case. This will be kicked out. Lambda will go down to 1, and you recover Hooke's law for 1D case, which we started with, where C is nothing but elasticity modulus, Young's modulus. And then for 3D case, you take this elasticity tensor, you build from lambda parameters lambda mu, or whatever it is that you want to build it. So we already mentioned that in 1D case, this second pure critical stress being connected with Young's modulus times the Green Lagrange strain, and the fact that you want to obtain the physics of what is going on by taking into account the something that looks like a true stress. So true stress or Cauchy stress has the same numerical value in 1D as the first pure critical stress. So recall the first pure critical stress was a lambda minus 1, that means 1 over lambda times P. So P would be equal to lambda times the S. So that becomes C times 1/2 lambda squared minus 1 times lambda. So obviously, when lambda goes to 1, this is fine. But there's a point of inflection. And basically, that has to be dp d lambda. So that turns out to be, can be equal to 0. And that results with when lambda goes to -1 large compressive strain, the stress simply remains 0. So basically, the idea here that you lose the convexity of your free energy should have been going upwards, but it's actually just turned out with the inflection point at the 0.577. And so up to then, let's say, constitutive model, even if it's not measured the same way the strain in compression tension, you can still say, okay, I can live with that. But after that, definitely I can no longer live with that, because it goes down to berserk. It is not physical that you can have a very large compressive strain with a 0 stress. That just doesn't exist. It's just basic consequence of a not well-founded formulation of this. So the question is, how the hell then I do a better job? So it was easy for John Ball to say, well, go back to the basics, and that means the intrinsic strain measures are deformation gradient, its cofactor and its determinant. So if you make a function which is convex, what does it mean to be convex? That means a function which has these arguments, which are one value is A1, the other one value will be A2. You connect these two by the straight line, which you can quantify by alpha times A1 plus 1 minus alpha times A2. And you want to make sure that this is small or equal to this same parameter alpha times psi of A1 plus 1 minus alpha times psi of A2, and then you are convex. So that's easier said than done, because in this type of thing, it becomes quite messy, especially for 3D case shells and stuff like that. So we need a somewhat different approach. And that's what I try to basically impose here. So let us first go into some kind of consideration what one should take into account when you're dealing with the large strains. Namely, you recall that one sure way of dealing with large strains is you go through polar factorization, and you present the deformation gradient as the product between rotation, which is a 2-point tensor, and deformation. So it could be the right stretch tensor, U, which is a material measure of strain, or it could be left stretch tensor V, which is a spatial the measure of strain. And then if you want to say express some kind of elastic response, you can then say, well, I need a function, sigma, to be a function of f and x. And then this sigma could also be expressed in terms of second periodic stress, in which case I need the function s, which could be a function of x and f. And connection between the two functions is always possible to establish given the connection between the true stress and the sigma and second periodic stress s. It goes through this determinant f, f minus 1, f minus transpose, and so on and so forth. So when building the constitutive model, typically, first, the restriction, if you want to talk about homogeneity, that means the properties of a material are the same in each and every point of the domain that this material occupies. It makes sense to talk about homogeneity only in the initial configuration, because in large deformation, given that you can have a very large deformation, let's say the large compressive or large tensile deformation, you then start having a strain field which is very much heterogeneous. That means varies a lot from one point to another. So you can no longer really observe homogeneity in something which is already heavily deformed. And then there are two axioms. So that kind of gears towards the applying, if you want to talk about homogeneity, it means you want to drop X, it has to be material description. But anyway, in solid mechanics, I've been talking all the time about material description. In other words, even if I take a Kirchhoff stress rather than second periodic Kirchhoff stress, it's still all function of the coordinates in the initial configuration. So that part is fine. Now, there are two more restrictions that I want to impose. I can talk about something called axiom of material indifference, and I can also talk about isotropy. Isotropy is easy. Isotropy means that simply you are taking the same behavior no matter what's the orientation of the line that you want to describe the behavior. So this recall when you had the linear elasticity small deformation setting, that simply amounted to taking two parameters for characterizing linear elastic response, not only in terms of Young's modulus, but also in terms of Poisson's ratio. Axiom of material difference actually means that if you have very large deformation, taking you from the initial configuration that we denoted as omega to the deformed configuration, which is denoted as omega phi, and then basically you have a new position vector x phi, and then you're computing the stress vector, which I call T phi. It is produced the true or Cauchy stress sigma phi times n phi, where n is a unit vector exterior normal. So that's the Cauchy principle directly applied to the deformed configuration. Now I observe that I'm sitting, let's say, on the left of this event, and somebody sitting on the right or in the center or wherever it is, different place. So his point of view could be explained by saying you have a rotation that is quantifying like a rigid body motion. So Q is just an orthogonal tensor. It does not vary from point to point because you're actually observing the whole deformed body in the same way. So basically, he doesn't see T phi, but he sees something that he called T psi, which is equal to this orthogonal tensor Q, quantifying the rigid body rotation times T phi. And then the whole point axiom of material indifference should actually mean that both of these observers, the one which is sitting in the central position, so doesn't have to incline his head, and the one who is inclining, rotating his head, because you need to kind of get rotation under control, you have a different point of view, they should come up to the same physical result. What it means goes as follows. If I want to express my, let's say, response of the material as a function of sigma of x and f being deformation gradient, the other guy should be expressing it as a proper transformation. We have Q being orthogonal tensor, which is giving a transformation from this, let's say, real deformed configuration to some kind of rotating point of view of this deformed configuration. So if you think of that, let's say the space occupied by omega phi and the space occupied by omega psi is the same space. It just has been rotated. So basically, this translation should go as such. And if I choose a special, let's say, choice of rotation that corresponds to the one in the polar decomposition, then I can write it in the reduced form as such. And then finally, it turns out that this is automatically verified if I now transfer this back to the initial configuration, I will have the axiom of principal material difference verified if my constitutive model is built not in terms of F, but in terms of C, so rotation is eliminated by using the right Cauchy-Green strain tensor, which is F transpose times F. So by this orthogonality to R, this simply kicks out. So this is really the kind of argument when I have this rotated configuration, the stress vector is equal to sigma psi times n psi. That should be my T psi. But then recall, this is simply Q times T phi because this has been rotated. And basically, T phi was nothing but sigma phi times n phi. Now, n phi was also rotated. And this is happened to be Q transpose times n psi. So when you actually gather all these things together, I have here a sigma psi, and I have here Q times sigma phi times Q transpose. And that's precisely this type of result that I take. Then I can take Q to be R, and basically you can simplify that. And at the end, the last result is, if you recall what is the connection between sigma and S, you can come up with this conclusion that axiom of material difference is verified if the constitutive model is built in terms of a second pure Kirchhoff as a function C, which happen to be, let's say, some Kirchhoff material because this is a system tensor times 1/2 C minus identity, so that's precisely the case. Now, this is one possibility. If I now go back to isotropy, that means you have the same response no matter what's the orientation of the fiber I'm looking at. So what we will do there, again, you can say, well, this different way of writing my constitutive model is given here, and I should have the same result even if somebody has different point of view of the initial configuration, and you have this rotation slammed on top of your initial configuration. So they should all be mapping the same deformed configuration, should all be mapping into the same, let's say, constitutive law that enters into this. So here you have a kind of a similar but somewhat inverse situation. If I really want to express the constitutive model, it has to be expressed as a terms of second pure Kirchhoff stress, which is function F, and the orientated configuration, which is obtained as a deformation of gradient times Q transpose. Again, Q is a orthogonal tensor, which gives me the simply rotation of this initial configuration. So initial configuration, which is sitting here, occupies certain volume, and the rotated configuration occupies the same volume. It has just been rotated. So deformation gradient takes you from this to that configuration, simply orthogonal tensor, with no change of distance in any of these points. Recall, this was the way you introduced the polar decomposition. And so basically then, if I take this rotation to correspond to the polar decomposition part, I can reduce the equation A to equation B. And then finally, it turns out that this isotropy criteria is verified if at the end I'm describing the, let's say, the stress response in terms of not of sigma function of F, but sigma as a function of B, where B is equal to FF transpose. So again, rotation is kind of kicked out. So this computation goes in a similar direction. We said we are computing your material formula of the traction, and then in the rotating configuration, this traction is equal to 2 transpose times n. That gives you a description from here and description from there. Then turning the Q into the rotation that features in the polar decomposition. You have the second line, and then finally recalling the correction between the second pure Kirchhoff and the true Cauchy stress. You can come up with the last result. All the details you have it in the book if you really care about looking into details. I refer this to look there carefully. So when all is said and done, we have one connection about how to write a sound constitutive model in large deformation. Elasticity is by material indifference. You have finally to write the second pure Kirchhoff is a function of the green on the right Cauchy-Green strain, which is F transpose F. And then isotropy asks that you write that the true Cauchy stress is a function of a left Cauchy-Green strain, which is F times F transpose. So what do we do now? Well, first of all, if I go into that, I can now go even further. I can say invariant measure of these strains could be constructed from so-called invariants of the deformation stress, deformation tensor like C. So basically, the invariants are the coefficients of so-called characteristic equation of the tensor C. If you're computing the principal values of C, you can take solve eigenvalue problem C minus some kind of lambda times identity times the eigenvectors, and then you'll come up with a characteristic equation which has a lambda to the power 3 plus first invariant times lambda square plus second variant times lambda plus the third invariant E3. So if you go through this development, and I think you have it in all the details sufficient in the book, you can basically write that first invariant is simply trace of C, and the second variant is trace of C squared minus trace of C squared, which is not the same thing. You first multiply C by C, and then you compute trace. And finally, the third invariant is determinant of your tensor C. Hence, I will then postulate the hyperelastic response in terms of these three invariants, and I will have already material indifference verified. No matter what's the coordinate system, these invariants are always the same. And if I postulate the range in terms of the three invariants, I'm fine with the computation of my stress. So how do I compute the stress? Well, I compute the second pure Kirchhoff stress as a partial derivative of this potential with respect to the Green-Lagrange strain. Green-Lagrange strain being 1/2 C minus an NT. So this is like computing derivative with respect to the C, and then multiply by 2, because that comes from this 1/2. So we'll need computation of the derivatives of these invariants with respect to C. It happens that the trace of C is just a C dot identity. So if you take derivative with respect to C, you come back with the identity. So here you again get your first invariant times identity from the first term, and from the second term you get C. And finally, the derivative of the determinant is equal to determinant itself times C minus 1. And so when all is said and done, I get that these terms, if I postulate free energy in terms of the invariance of the tensor C, I can simply recall that S is equal to these corresponding derivatives plus identity plus the derivative second invariant times C, and then finally derivative with respect to third invariant times C minus 1. So this will be one model which verifies the material indifference. And how about the other one? Well, if I take now the other model, first of all, I can recall that principal values, invariance of C and B, C being F transpose F and B being F transpose, conveniently happen to be the same. Basically, although the what you call it, the eigen values are not the same, the invariants are. And then basically you can say, if I know the invariance of C, I know also invariance of B. And then you can transfer this equation that we wrote previously by using the transformation for the Kirchhoff stress to be equal to F times second pure Kirchhoff stress times F transpose, and take into account what B and C are. And given that these partial derivatives with respect to the invariance with the vector of the tensor C are the same as the variance of the tensor B, I can add this equation here. So this is also a suitable type of equation which should handle the isotropy. So basically I can handle both of those. Now, the one that I'm advocating is not to go to computation of these invariants, but rather to stick to the principal stretches. What are these principal stretches? Well, if you take a polar decomposition theorem, you can split your deformation gradient into the rotation R and the stretch tensor U, which is on the right-hand side, or into the stretch tensor V, which is on the left-hand side, and the same rotation R. Now I can compute my principal stretches as the eigenvalues of my stretch tensor. In other words, I have to take a matrix representation of this tensor. This is matrix 3 by 3. So I can have three principal directions, lambda 1, 2, and 3, which will be computed. And every principal direction, lambda 1, 2, 3, these are stretches. This is the largest stretch, or the smallest stretch all the way to the largest stretch. And all of these stretches are accompanied with the corresponding direction, N1, N2, and 3. These three directions are orthogonal to each other and give you a representation of your stretch tensor. Now, given that the C is U squared, as much as B is V squared. First of all, I didn't mention that if you now compute the principal stretches from V, you're going to get the same principal stretches. The only difference is not going to be the same principal directions because these are in the initial configuration and phi are in the deformed configuration. So basically just taking the principal stretch and you're transforming it into the deformed configuration. But lambdas are invariant, so you can again, by taking the internal energy function to be a function of these principal stretches, you can basically satisfy both homogeneity and the material indifference type of axiom. So if I go back to what these, let's say, C's are, well, these are the first invariant. This is the trace of C that happen to be only lambda 1 squared plus lambda 2 squared plus lambda 3 squared. Because in this presentation, C, if you have a principal direction, is simply, well, it's first U. If you have a principal direction, U is equal to lambda 1, lambda 2, lambda 3, placed on the main diagonal. And then C, let me maybe just write this so we are clear on that, what I'm talking about. So basically here, when I have a principal direction, so this is my up. Let's say this could be the body, and then you are looking into, this is a position of the initial configuration, this is your X, and then you have your deformed configuration, something like that, and your position X phi. Sorry about lousy drawings. Basically, I can take this one here, and measure would be F is equal to R times U as a first choice. So use a stretch tensor, which is giving you the deformation measures here, or I can write it as V times R, the same rotation tensor, only with the stretch tensor on this one. So if I compute U in the principal direction, this will be simply lambda 1, lambda 2, lambda 3. And all the other type of terms will be equal to 0. So that implies that C, which is equal to U squared, for this same choice of the coordinates, which has this direction n, could be written as lambda 1 squared all the way to lambda 3 squared. Of course, there's lambda 2 squared top, and then all the others are 0. I would have write it down, lambda 2 squared, and that's it. So the computation of these invariants is very simple. The trace will be sum of these three, and then the second invariant would be what's written here is basically lambda 1 squared times lambda 2 squared plus lambda 2 squared, lambda 3 squared, plus lambda 3 squared, lambda 1 squared, and then determinant is simply the product of these three, that is lambda 1 squared times lambda 2 squared times lambda 3 squared. Hence, you can build the internal energy function as a function of these three stretches, and they can be featuring both initial or deformed configuration, doesn't really matter, because the computation of the principal value, which is the stretch, principal stretch, is invariant, whatever configuration that you're taking, which is kind of reassuring. So Ogden, in his book that he picked up from the notes of Hill, basically worked this in detail. There's like 400 or 500 pages with different type of choices. So typical stuff that you find is the internal energy being built as a function of lambda 1, lambda 2, lambda 3, this lambda 1, 2, 3 being principal stretches. So the more general setting would be to say that this could be lambda 1 to the power alpha r, lambda 2 to the power alpha r, lambda 3 to the power alpha r minus 3. All this multiplied by mu r divided by alpha r, and you have to have this restriction, the sum of mu r times alpha r equal to 2 mu, so you can get incompressible behavior. For this one, it's very easy to check that you are now fulfilling all these conditions which are physical. Namely, if you have a principal stretch going down to 1, you should have a 0 strain. So 1, 1, and 1, whatever is the power alpha r, doesn't really matter. This will be 3. 3 minus 3 is equal to 0. So the internal energy goes down to 0. So you're really sure that you are doing the right thing for the small deformation setting. And now if you take a lambda going to infinity, this explodes. If you take a lambda going to 0, this again making sure that each and every one of them is becoming to exploring to infinity, and basically that you are sure that you have a asymptotic behavior for large compressive, large tensile strain, which is just justified in physical. So if I choose to take this principal direction, how do I actually handle this? Well, I go back to my material description where the internal work of these forces was written as a variation of the Green Lagrange strain times the second pure kick of stress. And I have my linearization where I have a geometric part and I have my material part. So obviously, I know how to compute everything with the finite element discretization. I have already explained it on the illustration with the 4-node quadrilateral element, also with the 2-node truss bar. You had your small homeworks. So now the question is, if I have chosen to build my internal edges functional principal stretches, how do I compute now stress and how do I compute the corresponding modules? So here's the answer immediately, and I'll then explain in detail why is it so. Well, first of all, you compute your stress, second pure critical stress by definition as the derivative of your free energy potential with respect to E. And even though free energy potential is built from a lambda i's, you can say now I take a chain rule and I basically take a derivative of C of lambda I with respect to each lambda I. So that's a simple scalar computation. And I have to multiply each and every term with the corresponding derivative of lambda I with respect to C, where lambda I is the corresponding principal stretch. And that's the computation. I'll show what it is and just give you the result here. This is simply 1/2 lambda I, Ni tensorial Ni, where Ni is nothing but the corresponding principal direction for U stretch. The same thing will be for B if you go there, and so on and so forth. By the way, this is also principal direction for C. So both stretches U and C are based on the same principal direction. So I can compute this from derivative of eigenvalue problem. I'll show that how. And simply once I have it in the scalar potential, this is very easy to compute the components of the stress. I have something called spectral decomposition of the stress, and you'll see there will be something like a principal value of the second pure electrical stress that accompanying the corresponding stretches. And then the computational derivative is simply systematic application of the same type of results. So we were able to reproduce a really large deformation for both the rubber-like material to have kind of a realistic response implemented it correctly. So basically, if you go to this principal direction, you can write the easiest way of representing matrix representation of these tensors in terms of what is called a spectral decomposition. So you take the coordinates which are aligned with the principal directions in the material description and in the spatial description. In those coordinates, deformation gradient is simply a diagonal matrix with the principal stretches lambda 1, 2, and 3 placed on the main diagonal. And then basically, you can take rotation tensor to have this NE phi times NE tensor product, sum of these three, and basically with the eigenvalues equal to 1 because there's no change of deformation. So the stretch for the rotation is equal to 1. There's no stretch. The initial length is preserved to the deformed length, and that's what you got. The only thing is with the R, this is your 2-point tensor, so it has this NI phi. So now if I'm making spectral decomposition of the right stretch tensor, U, this will be lambda I, Ni, tensorial Ni, and basically this is now material version of that you can express in terms of your, let's say, base vectors. And of course, you can get the spatial version of that again that you express in the corresponding base vectors in the deformed configuration. Now, the spectral decomposition of this U could give me very easy spectral decomposition of C, given that C is F transpose F or U squared. That becomes simply lambda I squared Ni tensorial Ni summing up over these three values for lambda I. And basically, that's how you can do it. So the similar thing for B, I still have my principal stretches for V to be here in the spectral decomposition. The only thing now, they are unit vectors, principal direction in the deformed configuration. And B will be lambda I squared times the same tensor product of the principal direction in the deformed configuration. Going from one to another could be easy. Here you have an eigenvalue problem for your B, which is given that B is equal to FF transpose. I put it here. then I know that F is transposed as a RU or VR, so that V is equal R times U times R transposed. So I'm introducing this into the type of equation here, and I can recognize that this guy here could be written as a C minus 1. And basically that guy there could be written as Ni, so I can recover the corresponding Agolli problem for C. And in the process, I can obtain what is the connection between Ni phi and Ni, which is basically given in this line here. So I can write my, let's say, connection for all these spectral compositions for the stretch tensor, rotation tensor, and so on and so forth, and establish connection between the principal direction in the initial and the deformed configuration. Okay, when that is done, and I can now comment on different choices for this free energy function. So as I already said, is the most general case of 3D is given here with the restriction that sum of these mu r alpha r had to be equal to 2 mu, so it can cover incompressible material. So there's a Valanis who worked on that, and he introduced the hypothesis. This is way of writing this is to consider the potential in the direction of first stretch, and the potential in the direction of second stretch, and the potential direction of the third stretch. And then you can put it together. It's like if you're saying the first stretch will be lambda 1 alpha r minus 1, then second will be lambda 2 alpha r minus 1, and then third would be lambda r alpha r lambda 3 alpha r minus 1. So altogether they will amount to this type of thing. And so basically with the choice of this function phi, it has to be equal to 0 when lambda is equal to 1, which will be the case. The lambda minus 1 will be lambda minus 1, lambda minus 1. Then if you take first and second derivative, they have to amount to these 2 mu's. And now from 3D case, you can recover corresponding cases for 2D and 1D. 1D was the one that I was showing you for this cable element with the ordinary type of material. And 2D I discuss here. So you have either plane strain or plane stress case. So in one-dimensional case, if these two guys are the same, I can get my, let's say, lambda to be equal to lambda to my power minus 0.5. And then you have this type of result that I already use for, as I said, cable element. And then you can see that this behaves accordingly, namely when lambda goes down to 1, you have 1 plus 2. This is 3 minus 3. This is really getting down to 0. Then when lambda goes to infinity, this term explodes. When lambda goes to 0, this term explodes. So you have this asymptotic behavior, which is all correct. And this obviously satisfies all these convexity conditions that you can have for 1D case. How do you compute your stresses? Well, stress is a derivative of W with respect to E. That will be derivative of W with respect to lambda, because now it's function lambda times lambda E. But lambda is recorded E is equal to 1/2 lambda squared minus 1. From this, I conclude lambda is equal to square root 1 plus 2E. So the lambda D is simply equal to 2 divided by 2 times 1 plus 2E. And 1 plus 2E square root is nothing but lambda. So this is 1 over lambda. So at the end, it's very simple. Actually, I get S as 1 over lambda times derivative W with respect to lambda. So this, what was given as W, this gives me derivative divided by lambda. I get this. And then tangent modulus again, second derivative of this S or this W with respect to E, or first derivative of S with respect to E. So it becomes 1 over lambda d as d lambda, and that gives me the tangent modulus. So basically, this was the case. You can just take this nonlinear type of expression for the principal stretch, replace it in the Young's modulus for some anarchical material, and you have your nonlinear behavior of rubber-like material for the cables. If you have a 2D case, you have to distinguish between the plane strain with lambda 3 equal to 1. There's no change of thickness in the direction 3, and then simply kicks out, and you have this type of expression, or plane stress, in which case, on the basis of incompressibility, you can take the product lambda 1, lambda 2, lambda 3 is equal to 1. Hence, that allows me to write the lambda 3 is equal to 1 divided by lambda 1 times lambda 2. And that basically amounts to saying that the potential of psi of lambda 1 and 2 could be written this way. So I have all different type of cases, 1, 2, and 3D case, and I can then know how to compute my corresponding stress. And the question is, okay, how to compute my tangent modules? So we already said the computation of the stress is given as the derivative of the potential given in terms of these principal stretches. Here I do it for 2 decays, so that becomes 2 times the rate of side factor C. And basically that amounts to saying computation this with respect to the principal stretches, lambda 1 and lambda 2, times the lambda derivative of the lambda I, either 1 or 2, with respect to psi. So how do I compute this guy? Well, I go back to the eigenvalue problem that C minus lambda I squared identity times Ni is equal to 0. Then I take a directional derivative in the direction C. That means my perturbation C small index epsilon. This is not strain, this is just small parameter epsilon. Sorry about this notation, but what the hell, there are only so many letters. Epsilon often is used for very small parameter. So this is C plus epsilon times dc, like an increment. Then I can take this one to be dc. This is the fourth order identity tensor times dc minus the derivative of this is 2 lambda times the lambda dc dot dc and e, and this one will be d and e. Then I dot this with identity nj. So all the other terms will disappear except for the one where I and j are the same. So that amount saying I have here dc ne dot ne, and basically I have there 2 lambda d lambda e dc dot dc, and here ne times ne. So basically this one will be kicked out because again, eigenvalue problem applies, and I'm only stuck with these 2 terms. So if I look what it is, you can add this as ni tensor ni dot dc. That's the way you can write as well. And here you compare this against 1 over 2 lambda d lambda dc dot dc. So basically, by comparing these terms that have to be equal to 0, I can conclude that my lambda e with respect to dc is equal to 1 over 2 lambda e ni tensorial ni. And then I can use this in my computation to obtain the spectral decomposition of the second polar Kirchhoff stress with the principal values of this stress that I compute directly from the potential. So the compute is 1 over lambda e, derivative of this potential with the principal stretches. So that gives me SE, which is written here explicitly. And then you have this tensor product NE and E with spectral composition. If you have like a 2D plane stress, that becomes something like this, given here explicitly. And that's what we use in one of the papers with Friedrich Gutmann, a friend of mine from Germany, when we were both at Berkeley, to have this rubber-like shells and things like that. So then if I want to carry on and do computation tangent modules, so tangent modules is a DSBE, where S second polar Kirchhoff and E is Green-Lagrange strain. For simple cases of some Kirchhoff material, they simply cancel system modules. For the case when you have this free energy done in terms of principal stretches, well, it's a little bit more complicated. You have to carry on computation of the material part and computation of the spatial part. So computation of material part, you have you just had the principal expression for the stresses, so you have to do computation of this one. So basically that amounts to saying you have a dsdc, where you just had it already. So this is dsi d lambda j and d lambda j dc. So that amounts to 1 over lambda j times dsi d lambda j. This will be your elasticity modules in the direction of the principal. This will be something like in 3D case 3 by 3 matrix, in 2D case will be 2 by 2. In 1D case, obviously, it was just one component. And here you have Ni tensorial Ni, and then tensorial Nj, tensorial Nj. So this is your fourth order tensor, which gives you the elasticity tensor to fill in the material part. But you also have these principal directions turning from one step to another. So you have to take derivative of this principal direction Ni tensorial Ni with respect to tensor C. And so basically this is just to recall what is this for the plane stress. And here I need the direction of this principal direction turning for the case. So basically I go back to a spectral decomposition of my C deformation tensor in terms of the principal direction. So this is lambda 1 squared, Ni tensorial Ni, and 1 tensorial N1, sorry, plus lambda 2 squared, and 2 tensorial N2. And identity would be the same thing, only instead of lambdas, you have just ones. So with these two together, I can write that C minus lambda 1 squared identity is equal to this. Hence, N1 tensorial N1 could be expressed as 1 over lambda 1 squared minus lambda 2 squared, C minus lambda squared, lambda 2 squared identity. So when I'm now taking derivative, which I need to take here, basically it reduces to taking derivative of the terms that I was doing. This is a little bit long, but at the end is really quite straightforward. That at the end I get the derivative of N1 amounts to this story, which is 1 over lambda squared minus lambda 2 squared, identity minus N1, tensorial N1, and so on and so forth. I have to say that many of the things what I was doing is, first of all, when I was a co-protocol for the Andalusia, doing this large rotation stuff, in which case I did not have my own PhD students, but I was my own research team. And I surprised myself that I could do one paper in 1 week because nobody was bugging me already to talk about it. And then in comparing let's say the first period I had 5 PhD students, and some of those things I could still do by myself and then work it out and then still could do implementation. It looks kind of scary because people don't like this juggling around, but it's fairly easy. I then talked to many colleagues who are proficient by using this manipulation software like Mathematica or Maxima, some people like that. And turns out sometimes they cannot really catch the main thing that I keep repeating over and over again. So when you get really good in developing all this, it's not so scary. They're just long, but there are 2 or 3 tricks and you're repeating it systematically. So there's no big deal. So when all is said and done, I have my total elasticity modulus instead of some anarchical material, but this is constant given in terms of lambda parameters. Here I have this material part, which was written, as I said, for the, let's say, plane stress organic material, explicitly in terms of these parameters, mu r and alpha r. And then I have my geometric part, which is S1 minus S2 divided by lambda 1 squared minus lambda 2 squared with all these things here. But these are all tensor developments. Now, if I want to do finite element implementation, I'm packing these tensors into the vectors and matrices. So first thing, I take these 3 components of a strain, E11, E22 times E12, and the corresponding 3 components of the stress S11, S22, S12. I take my principal direction. So in 2D is nothing but the cosine and sine of the orientation. And then in 2 will be equal to minus sine and cosine, because these 2 have to be orthogonal. Then I compute the first invariant, second invariant, and I obtain my, let's say, this invariance here, and I can write what Ni is. And basically, I can do the spectral composition with the principal direction of S that I compute directly from a given potential. And I, that amounts to saying we have a transformation matrix, which is written as cosine squared, sine squared, sine squared, sine cosine minus sine cosine, times the principal direction of the second pure Kirchhoff stress, S1, S2, that you compute from the potential. So this is all packed. Here you have a principal direction, 2 components only. You have this transformation matrix that becomes on the function of the current orientation of the principal directions, and you obtain your 3 physical values. Granular Lagrange strain is packed in the same way. As much as I have these 3 physical components in XY space, I also have 2 principal components in the principal direction, E1 and E2. And basically, the connection is given by this transformation matrix T only transposed. Then packing the geometric part of the tangent modulus, which was written here, a long expression. Basically, I had to say what was that the C was cosine and sine and so on and so forth. So that amounts to saying, here's your identity, is 1, 1, 1/2. This could be like this C squared CS transpose, and this could be the other one, S squared, C squared, etc. And then turns out when you work it out in detail, this could be written as 1/2 G times G transpose, where G is equal to minus sine or 2 alpha plus sine of 2 alpha cosine 2 alpha. Alpha is the orientation of the principal direction. So at the end, the tangent elasticity tensor is written as the one that they computed the principal direction and filtered with T and T transpose, and the geometric part, which is S1 minus 2, lambda 1 squared minus lambda 2, GG transpose. One has to worry about when you have a limit case when both of these are the same. You have something in terminus we have to do with asymptotic development, and these are kind of details to worry about. You have this in one of these numerical journals that we've done. So this is all about elasticity. Now you can also do next step, which would be like going into all the way to plasticity. And basically, it could be interesting maybe to try to give you a little bit exercise here. But what else? It could be well, the homework that I gave you the last time. Let me start to do that up. So that was the question that I had pre-stressing here. And I introduced this to be, let's say if I have pre-stressing, which is equal to L. So basically I'm really stretching it. And here you have now the Ogden material. C is equal function of lambda. So this is now a rubber-like material. Basically, you're stretching this into the 2 times. And then you have like a initial stress there. And then you're applying some kind of a distributing loading. To obtain the corresponding deformation. So you can take any load here just to see how this computation work. So basically, this will like first you have to get into the corresponding value of your let's say material. You will have a rigidity because of the pre-stressing, and then you can do the computation of the thing with the as you go along to get this under control. And so basically, this is really the idea that and what else? I have been doing here. This is like a small homework here, one, and then this paper we're doing in a finite element analysis and design. What about if I have membrane like this? So this is membrane placed in 3-dimensional space, and this is again rubber-like membrane. Only this time around is the free energy is a function of lambda 1 and lambda 2. This is plane stress case. So how do I compute S in any Gauss point? So imagine these are particular points in particular Gauss point. So the question is how to compute S given that I have a curvilinear space. If I cut it like that, here this will be curvilinear. If I cut it like that, this will be curvilinear. So the question what it is that I have to do. So I already explained this for the rubber, sorry, for the cables. So if I want to do this membrane, I can say here I have a global coordinate system with these vectors EI, and these are coordinates XI. And on the other side, for every point here, I can take S1, and I can take S2 to be a local Cartesian coordinates. And then I do transformation from this global system to 1, and I do transformation to the natural coordinate system from this one. So the question is, how do I actually get the computation when I have a curvilinear shape of this membrane? And so give me how to compute my S for every point that I want to compute. This is something that would be worthy of your thinking, and if you have difficulty doing it, I didn't put in the book where you can check this paper that is done with Friedrich Gutmann and some other papers. So you have this terminology of principal directions in the curvilinear space. So it becomes really handy in this case. I mean, turns out you no longer need curvilinear coordinates, even if you deal with something which is a 3D space curved surface. You can always simplify computation by taking into account the local Cartesian system and then doing the computation inside this local Cartesian system. So the only trick is like, how do I compute d over ds1 or whatever is that I'm trying to compute, displacement and so on, and d over ds2. So basically, this is so just to give you a transformation, I can go to local to global into this one here, and basically I can establish very easily this one to that one, and I can establish very easily this one to that one. This happened to be only rotation, so this is your orthogonal tensor Q, and this has to be done with the isoparametric mapping. So what I need S of psi will be obtained as a composition of these two mappings. You know, if I want to go from here to there, I can either go from there to there and do the composition of these two mapping, and I get my result. So this is as much as I wanted to indicate. And if you're into this business, large deformation, I think one of them mentioned that you have large deformation stuff. You have to handle this. Okay, so let's go back to to this one. So the next step would be to go into the plasticity at large deformation. So what should be the plasticity large deformation? Well, there was lots of works on the plasticity large deformation. There was actually the first work was of E.H. Lee. He was a professor at Stanford, and Mandel was a professor at École Polytechnique in France. In the 70s, they wrote the books on all on papers or lecture notes discussing these different things. And there was really lots of what you call it, issues about this large deformation plasticity, whether it's applied, whether it doesn't apply, and stuff like that. And then this book on manifolds for elasticity, Marsden and Hughes, was being written in early and late 80s. And then at that time, these guys were lucky. Simortis and stuff, they were actually PhD students at Berkeley. So they were reading this book as a proof, and they get all this manifold directly from these guys who was developing them. And then they apply this manifold story to large deformation plasticity. So honestly, if you look into the first papers with this covariant formulation and all kind of stuff with tangent bundles, cotangent bundles, it's not an easy reading. If you try reading those papers, you really have to have like a special vocabulary that comes from these things. So then at a certain point, when I worked on that, especially in the peaceful time in the PFL, lots of this work was done there. I actually pushed this development of the principal directions all the way to the end. And at the end, it's really a very simple story. It's no big deal. And that's so there's some of these papers that are equivalent to O'Leary Lagrangian formulation, fine definition plasticity. It was published in this theoretical journal, Solid in Structures. It was at that time very prestigious, even still today. Then the numerical implementation was done probably in the best computer software type of journal, Computer Methods, Applied Mechanics Engineering. And then a little bit, let's say, more practical orientation that was done in computer and structure, because that engineering profession is looking into that. What we introduce here is we try to construct a theoretical formulation of plasticity, viscoplasticity, large deformation. We introduce the idea of intermediate configuration where large deformation that are elastic and plastic. And we generalize kinematic hardening of Prager-Ziegler to large deformation. And we try to introduce this time integration scheme for stress computation so that you get a simplification for the principal axis method of Hill, and especially how to compute with tangent stiffness and whatnot. So basically, this is the part which was done initially by these guys. They said, if you want to have both a large elastic and large plastic deformation, contrary to many guys who are doing, for example, I mentioned already this Greco, the group of laboratories put together with the Lemaitre, they were simply splitting the elastic and plastic deformation rate additively. And actually, it's just not the way to do. Even actually, I took once a course with Nagdi, who did this work on shell, and they were like, kept saying that everybody is wrong. He had a very large paper, 90 pages. It says a critical review of finite deformation plasticity. Well, basically, in the 90 pages in general elasticity, so that paper on plasticity and general elasticity already funny. And then in 90 pages, you just say how everybody else is wrong. So when I took a course, he kept repeating this parental Royce, which is small deformation plasticity, like von Mises. And then we never explained how he would do it unless you do this additive decomposition. But basically, the other guys were wrong, and they were advocating multiplicative decomposition, which is here. You have your deformed configuration, you have initial configurations, initial is here, deform is there. So strictly speaking, if you're talking about manifolds, this should be the tangent space of the initial configuration, this should be the tangent space and deformed configuration. And then unloading, and they argue you cannot unload, but it's not really unloading. In reality, this is local unloading. So you can simply say that how you measure elastic and how you measure plastic deformation. So unloading is bring you this elastic deformation gradient, and this gives you plastic deformation gradient, and the spirit of large deformation, the coupling these two is multiplicative, just like a polar decomposition. So that really never went down clearly, but in fact, it's not that complicated. I mean, this is the trick I discussed with the late Matt Crisfield, that at the end worked it out in a way for those people who don't care about manifolds and how you do it. Imagine you have large deformation, okay? And so first you have a bar which is of the length L. And then you stretch your bar a lot. This is now your L phi. And if everything is homogeneous, which doesn't have to be the case, you know that lambda is equal to L phi divided by L. And this is already the intrinsic measure of deformation. So in order to stretch this, of course, you need a sigma, in particular sigma phi, the true or Cauchy stress, and happens to be larger than the yield stress. So you're plastifying. You stretch it so much that you started plastifying the thing. So they say, okay, basta, this is my loading program in terms of the application. You know, this is I apply up to a certain point and then I put it down. So this is, let's say, the traction or that gives you the stress. And this is your time. And so first you kind of do it up to the maximum value, and you pass in the process sigma y down the cross section, and then you reduce it down to 0. So when I unload, here was sigma was equal to 0. I started just applying the load. This sigma produces this any point sigma phi that is large. And then I unload here, finally, there's no sigma. I removed it. So sigma is equal to 0. Nothing going on, but the bar is no longer the same length. It has the length that I can call now LP. This is the length which became modified by the plasticity. That would mean LP. So when I do this, I can say, okay, lambda, which is equal to L phi L, L phi being the form length with the maximum value of the load that applied, L being the initial length, can also be written as L phi divided by LP, and then LP divided by L. I did not do anything. I just simply divided and multiplied LP so they can cancel. I can get back here. But I don't want to do that because I can now recognize that what transfers me from L phi to LP, recall here there was like a tangent space at initial configuration, and there was a tangent space in the deformed configuration, omega phi, constructed around a particular point. And so that takes me here with deformation gradient. And then I introduce some kind of intermediate configuration where basically with this intermediate configuration, I load, so I have a FEFP. And so that precisely becomes that. So going from L phi to 1, basically this becomes lambda E, because this is precisely how you obtain difference between L phi and LP by elastic unloading. This is part here. And then what is LPL? This is the part which I can never recover. This could be a plastic stretch, which is called lambda P. So this is first part of the idea that I want to explain. And that is really like corresponding here, the total deformation gradient. These are the results that are introduced by H. Lee and Mandel, that this is a product between FE, These are now tensors, so this is product these two tensors, and these are just scalars because it's one 1D case. So this is the first idea, that this simply reduces to 1D case to something you can really quantify, and that should be done in this manner. And you can always unload it. There's no problem of going there. So criticism of 3D case that you have to go and you cannot do it and stuff like that certainly will not apply. The second idea was if I now take something which is called a logarithmic strain to be my deformation measure. So by taking this, I can say that logarithmic strain lambda is equal to logarithmic of lambda E lambda P. And by definition of this logarithmic function, that becomes logarithmic function of lambda E plus a logarithmic function of lambda P. I'm missing my ln here. Okay, boop, boop. And so basically, sorry about this, let me write it again, not confuse. So basically, that amounts to saying that is the saying that total strain is equal to elastic strain plus plastic strain that we inherit from a small deformation theory. So with this approach with the principal directions, it's very convenient. You take a geometrical nonlinear effect by computing principal direction and then defining your strain energy in terms of the logarithmic strains. You can then recover what you've done in the small strain setting. The only difference is that you adapt your computation to the principal directions as opposed to the, let's say, small strain setting. You typically do it in physical coordinates. But there's really no big deal in adapting those things to a special choice of coordinate system once you do it. And that's actually how you can do this large deformation elastoplasticity in a very clean way and doing that. So this is kind of the idea in the nutshell. And we take a break here. And basically, when we come back, I'll go into details on how this is done and what you can do in terms of this computation and so on and so forth. So do you have any questions or comments before we break? Or
Hi, Professor.
So we come back to this more general case than 1D problem that I just described, how this multiplicative decomposition of the deformation gradient into elastic and plastic part in 1D becomes a simply multiplicative decomposition of the total stretch, which is ratio of the deformed versus initial length, if everything is homogeneous, into the elastic and plastic part. Of course, if it's not homogeneous, you do this locally. Lambda is dxy divided by dx. And then you can do for each and every point corresponding elastic stretch and plastic stretch, and so on and so forth. So basically, this is the kind of thing that we want to elaborate upon when we deal with the plasticity. So next to the elastic deformation, we are now introducing the plastic deformation. And basically, conceptually, what we're trying to see is that if you can deal with this plastic deformation in a way which would, at each and every point x, where we're following the motion and the deformation of the body, imagine the possibility of introducing this local unloading. And in the process of local unloading, that means we are introducing the intermediate configuration. Now, configuration may be not the proper word because a collection of these, let's say, the unloaded points is not a real configuration. It's just what is going on locally. But that fits with the description of how we deal with the plasticity computation in the finite element setting. Namely, recall when we are computing the equilibrium equation or go to dynamics, we have a dynamic motion equation. We are doing a global computation, but when we are computing the plastic deformation, let's say, or hardening variables and so on and so forth, these are just local computation. So it's not the question if intermediate configuration is the collection of compatible neighborhoods, because they have never been tested in each and every point in time. This is really consistent with the type of discretization, the finite element that you do, observing the internal variables locally, so you can complete the situation each and every finite element, and then we do collection of these finite elements to redistribute the loading in this particular case. So question of this compatibility which has been raised with the people who are doing just theory and not really numerical computation is, I would say, not pertinent much into this particular case. But people doing micromechanics, for example, a very famous paper, Taylor in 38 and then Asaro 79. Basically, when you have this type of plastic crystals in this micromechanical models, you in the initial configuration, you're getting the orientation of your crystals, and then you do the deformation. And when you unload, basically, there's a fairly sound way of splitting this into plastic and elastic deformation. The only thing I remember, Asada was doing this with the people from Brown again, and they were typically very much inclined to do viscoplastic rather than plastic deformation. But the whole point is they are doing the plastic deformation gradient typical of the slip system that is S tensorial N, which is like, mode 2 type of slips and characterizing the plasticity of metals. And then you can justify also this multiple decomposition from basically the micromechanics as well. So to develop this formulation in large deformation setting, we won't worry to start with about any hardening. We'll just take what we call perfect plasticity to start our developments for plasticity. Remember, in the small deformation setting, the only difference now will be that we are not talking about small, we're talking about a large deformation setting. In other words, we admit that there's a deformation gradient, which is taking you from initial configuration to very different deformed configuration. And then when you unload locally, you can recover what is elastic and remaining part of the plastic deformation gradient, such that these two are multiplicative and give you the whole product. So now, if we assume isotropy, recall isotropy would allow you to quantify the behavior of material for any direction that you chose, and that behavior should be the same. That would imply that Fe has to be properly transferred when you superpose the rigid body motion on the initial configuration and into Fe Q transpose, where Q is some kind of rotation tensor which leaves the initial configuration completely the same volume, just changing the orientation. It so happens that if you want to be able to verify this from the start, it's a similar thing that we've already done for the elasticity. You actually have to define your response not in terms of F, but rather in terms of B, where B is F transpose. But in this particular case, it's not going to be just F. The total F is just elastic part. So you'll talk about elastic left Cauchy green strain, which is equal to Fe transpose. And basically, you can then verify objectivity directly because Q being orthogonal tensor, it just kicks out. So you can have your internal energy functional B, which will be the same as a function of BE plus being the superposed rigid body rotation on the initial configuration. In the absence of the plastic flow, you will recover completely your elasticity with such an approach, and then basically you can deal with that. Then second one is objectivity of the elastic response under the rigid body motion superposed upon the current configuration, in which case you have to have a Fe to transform with the proper way from the orientation, from the changing the look on the deformed configuration with the rigid body rotation Q. So Fe plus, that means rotated configuration, should be equal to Q times Fe. Hence, you can then define all the strain energy to deal with that in terms of invariance. And in particular, we already advocated instead of using invariance, we just take the elastic stretches that I illustrated only for 1D case, what that means. This is the ratio between the deformed length and the unloaded length, and make internal energy a function of these elastic stretches. So how do I compute my elastic stretches? Well, I take elastic left Cauchy green deformation tensor, and I compute eigenvectors of this tensor, and I get my elastic stretches accompanying with the principal direction of such a stretch tensor. So this is the way I can write a spectral decomposition of the elastic Cauchy green strain tensor in terms of the elastic stretches squared times the tensor product between these principal directions of the elastic deformation. So then this would be one way of setting the eigenvalue problem. I want to show that basically you can do the same eigenvalue problem resulting with the same eigenvalues, which are elastic principal stretches lambda E I, for I equal 1, 2, and 3. If you use not elastic deformation, but plastic deformation, namely you do the pullback, you transform everything into the initial configuration, recalling that you have a multiplicative decomposition of the deformation gradient to FE, FP. So instead of the first part, you get something FP transpose FP, everything to the -1. So this FP transpose FP, you can call something like a plastic right Cauchy-Green tensor, inverse of that. And then basically this identity tensor could be replaced with the C-1. So you can see that the C-1 being the total Cauchy-Green right deformation tensor. So you can see in this particular case, this is now material representation of the same eigenvalue problem. C is playing the role of the induced metric in this configuration. So basically, if you want to do, let's say, a material representation of your stuff, you have to be able to quantify the metric with the total deformation tensor, and you have to be able to quantify the plastic deformation with this plastic deformation Cauchy-Green tensor inverse of that. And then basically you can work it out now in the material description and get some kind of, instead of standard eigenvalue problem, with this being identity matrix, you have some kind of generalized eigenvalue problem with the matrix pencil, what is called in the book of Parletto, and these two tensors or matrices. Please recall that it's always guaranteed that these lambdas are positive because these are principal stretches, and basic theorem says that these two are definitely positive, so C is definitely positive, so is a GP, you're guaranteed to have that. So I can quantify the behavior of material in terms of some kind of internal energy density, which could be the function of these principal elastic stretches, lambda I, E, or BE, or the pair of tensors C and GP. You have really different pictures the way you want to choose them, but let me stick with the lambda E, the principal stretches. So if you go back to thermodynamics to define dissipation for this perfect plasticity model in large deformation setting, you can say that dissipation is a difference between the stress power. This is the product between the energy conjugate stresses, in particular here second pure Kirchhoff stress, and the derivative of Green-Lagrange strain, which amounts to saying 1/2 C dot, minus the derivative time derivative, material time derivative of the internal energy, which here you keep as a function of C and GP. So you can say this is a partial derivative with respect to C times C dot, and this is partial derivative of GP times GP dot. And so basically you can say, if you have a simple case of the elastic process, internal variables, in this particular case, the plastic deformation is frozen, so GP dot is kept equal to 0, and I know dissipation should be equal to 0. So basically I get my stress to be described as a partial derivative of this potential with respect to C, and the only difference from the total, let's say, deformation when being elastic, here occurs the elastic principal stretch rather than the total stretch that you have. But very similar, if not the same results, could be computed for this case, just like we've done in detail for the elasticity part. Now, in the particular, for example, derivative of the lambda E elastic respect to C is equal simply to lambda E elastic divided by 2 multiplied by C-1 n tensorial C-1 n, and this could be worked out directly from the eigenvalue statement derivative of a particular case, and that's really very similar development to that. So you have an eigenvalue statement which is here, so I take a directional derivative in the direction of DC, so that gives me the first term, the second term, and this one here, then I multiply with NG, J being to 1, 2, 3, all the way to final value 3. So the only thing which matters is that J and I are the same. That eliminates this term and gives you the corresponding remaining terms here, and then you can obtain that this result that is a, let's say, the generalization of the case for the elasticity. So basically, I can at the end also have my spectral decomposition of a second pure Kirchhoff stress in terms of the same induced metric, and tau I being the principal values of the stress. And at the end, when I write it down this way and take into account how you actually write it here, you can conclude that the principal values of the second pure Kirchhoff stress could be directly computed for this potential as the partial derivative with respect to the elastic stretch multiplied by the elastic stretch itself. And that would be the way you can compute your stress. This is basically further observation is that partial derivative with respect to C and the partial derivative with respect to GP, because here you will need a derivative with respect to GP in this term here, are connected again through this eigenvalue statement. And you can show that the partial derivative with respect to C is basically C minus 1 times the partial derivative with respect to GP times GP. And that's what you're using here. Namely, in the plastic process, you still say that these constitutive equations are valid, so kick out that, and you have to compute this term. So use this result that I just explained, and you can write it this to be equal to, putting this on the other side, to be equal to C times S times GP minus 1. And here you have 1/2 GP plastic dot. So basically, I can write it also this way, putting this on that side. And I can say that this particular case, the plastic deformation is the dissipation is something which is positive. I now know it's an inelastic phenomena, it's a plasticity. So when I have this dissipation defined, I can appeal to the principle of maximal plastic dissipation, unlarge deformation, but it doesn't change nothing. I can say that the things start going plastifying, then the plastic dissipation will be maximized. That means minus plastic dissipation will be minimized. And that has to be done only for the admissible values of the stress, which is defined by the corresponding plasticity criteria, phi of S and C metric, multiply here by the corresponding plastic multiplier, where you actually turn this into unconstrained minimization for any value of stress. So the evolution equation can be obtained simply by computing the partial derivative of this plastic Lagrangian to get this contribution of 1/2 C GP dot GP minus 1 plus gamma dot d phi ds, from which you conclude that GP dot is equal to 2 times gamma dot C minus 1 derivative of phi with respect to S times GP. And then this is accompanied with the corresponding loading unloading condition. For the case where you have plasticity, phi should be equal to 0, gamma should be positive. And for the case when you don't have a plasticity, phi should be negative and gamma should be 0. So the product of gamma dot and phi is always equal to 0. If I have viscoplastic, I can change this slightly. I can then accept the positive values of the yield condition, where phi hat of essence C or phi of tau I being the principal of this second polar Kirchhoff stress, could be accepted to be positive, and that's actually what is producing the dissipation. So in this case, I call this viscoplastic dissipation. So instead of being GP, this is now GVP, like viscoplasticity, to the minus 1 times 1/2 G viscoplastic dot. I can write it also this way, where S is pulled out completely, and I go now through the maximum plastic dissipation or viscoplastic dissipation principle with the penalty version. In other words, I'm enhancing minus D viscoplastic with the quadratic term in terms of this chosen yield function, so that this is done for a positive value, and you don't touch it for the negative or 0 value. And this penalty term is typically related to the viscosity coefficient, the style of Pergina model, only taken to the larger deformation setting. So basically, the derivative of such a potential that is used as a penalty term is this Macaulay bracket divided by eta. So actually, we have something like an evolution equation for viscoplastic deformation, which is written in the format which is very similar to plasticity. The only difference being that for plasticity, gamma dot is computed from this consistency equation, whereas for viscoplasticity, you have this direct computation given the positive value of phi, filtered by the Macaulay bracket divided by eta, and then you have an evolution of your viscoplasticity. So you can write this evolution equation in terms of principal axis. You recall that the stresses S also share the same principal axis, and so you can then express all these guys in terms of principal axis. And so it happens that the GV plastic dot is equal to minus 2 times positive value of phi divided by eta, plus sum from I equal to 1 to 3, d phi r dt tau I, the tau I being the principal values of the second polar Kirchhoff stress, times C minus 1n tensorial ni, all this multiplied by G viscoplastic. So integrating this equation, you can do in many different ways. When we started this, we did it with the Euler forward or a little backward and stuff like that. Another way, if you deal with tensors and you want to take into account something like J2 plasticity, which was the initial objective of our work, very convenient integration would be to go through some kind of exponential mapping. Namely, if you have a function x dot equal to a of x and x of 0 equal to identity, you can basically write this in terms of exponential approximation, that you say x of t is equal to exponential at, where this exponential could be written in the closed form to be identity plus 1 over n times dA all to the power n. So this is like infinite series and stuff like that. Very similar exponential mapping is used for rotation when you talk about beams and stuff, these type of models. I'll mention that further. So when I take all these results into account, I can write now the viscoplastic deformation as exponential minus 2 positive value of phi divided by eta multiplied by the sum from I equal to 1 to 3 d phi d tau c minus 1 ni tensor ni. And basically this allows me to show that I can actually impose plastic incompressibility by taking into account something that like a yield criteria, which has this type of feature that d phi d tau I is equal to 0 when you sum it up. And that happens to be the case for the von Mises plasticity, which could be expressed in terms of the principal values of the rhetoric stress, which you can compute as the principal value of total stress minus 1/3 the trace of these values there. So this automatically gives you the possibility to check that the determinant of GVP is equal to 1. And given the GVP could be obtained as a determinant of FP squared, because this is FP transpose, basically you can get this one to be equal to 0. That means with the exponential approximation of this equation, you enforce plastic incompressibility exactly. So you don't have to worry about that one. And it could be important if you have very large plastic deformation to be able within discrete approximation to enforce some kind of important physical property, just like would be the plastic incompressibility. Of course, then you have to worry about how to construct the finite interpolation to handle the incompressibility and so on and so forth. Now, if I'm not happy with the perfect plasticity because it said everything is but perfect, it doesn't have much predictability because typical material would have a hardening phenomena. Now you want to put on top of this perfect yield function, which has only like compare the derivative part of stress with respect to 2/3 of the yield stress. You want to put your hardening for. Basically, we discussed two types of hardening. We discussed the isotropic hardening, where you need a variable psi, which could be equivalent plastic deformation. And we can discuss also the kinematic hardening. So for this particular case, kinematic hardening would allow you the cyclic deformation. And you assume that there's some kind of hardening variable, which is sort of a strain-like, which is proportional to the plastic deformation. So there's a C, which is a constant of proportionality. And so when you say proportional, that means both GVP and hardening share the same eigenvectors. So I can write this C minus ZI squared, C to the minus 1 as a metric, all multiplied by Ni equal to 0. So Zi are principal values of the back strain that is conjugate to the back stress. So back strain is called Xi, and back stress is called A, and the principal values of this back stress is called alpha I. And again, these guys share the same eigenvectors like strains and let's say so everything is done in terms of these principal directions. And so the yield criteria could be simplified into the part where you have this, what you call it, the principal direction of a second polar Kirchhoff stress, the principal direction of the back stress, and eventually the hardening variable, which is giving you isotropic hardening. So basically, then I go back to second principle thermodynamics to define now dissipation for this more general case. So it says again, dissipation is either positive or 0, and it's computed as a stress power, which is product between second polar Kirchhoff stress and the time derivative of the Green-Lagrange strain, or 1/2 of the C dot. And basically minus the material time derivative of the eternal function, which is now a function of the plastic deformation, back strain deformation, and the isotropic hardening type of variable. So I again take all these partial derivatives into account and distinguish between the elastic process where all the internal variables are frozen. That means GVP dot is equal to 0, FEP dot is 0, of course. Then the back strain Xi dot is equal to 0, and the hardening variable log psi dot again is equal to 0. So from this one, I can obtain all these drops, and I can obtain constitutive equation, which says that the second pure Kirchhoff stress is the derivative of such a potential with respect to a green Lagrange strain, or 2 times derivative with respect to the Cauchy-Green right deformation tensor. And I also introduced the conjugate variable to a hardening variable. Little q is equal to derivative of this potential with respect to a lowercase psi, isotropic hardening. And of course, I can introduce the conjugate stress, which is called back stress, to the hardening strain for the kinematic hardening, which is uppercase psi. And basically, I write the spectral decomposition of the back stress, which is a kind of the same format as the real stress. We have like these principal directions are computed from the derivative of the potential with respect to the principal, with the spectral decomposition computed with the principal direction of the back stress Zi times the derivative of the potential with respect to the Zi multiplied by C minus 1 and I times over C minus 1 and I. And so these principal directions are simply equal to Zi derivative of the potential with respect to Zi. And I also have that partial derivative with respect to C and respect to psi are connected. That's what I'll need in the next step. So when I'm doing my, let's say, viscoplastic deformation, that means I'm going into the computation of viscoplastic dissipation, and I do that with a penalty term, where I assume that yield function is like used as a penalty term, and it's used only for the positive way, so it's 1 over eta times the yield function squared and 1/2 and so on and so forth. So when I take derivative from that type of penalty term, I get my Macaulay bracket, and so I can see if I have a derivatives of these regularized potential, which is viscoplastic deformation plus this penalty term. From the first term, I recover the evolution equation of the viscoplastic deformation to be expressed this way. So that is close to this, if not the same, to this perfect plasticity. But now I get two novelties. One is the evolution equation for this back strain to be expressed again in terms of the this format. And then I have an evolution equation for the isotropic hardening variable. All these equations could be written in the principal directions. In particular, if I take the back strain, this is written this way, and I can then obtain the corresponding result for the evolution we did. And given the account that I have a back stress to be purely deviatoric, with the alpha 1, alpha 2, and alpha 3 being the principal values of the back stress, sum of the three equal to 0. Basically, I can show that I have a plastic incompressibility preserved also in this case when I assume the kinematic hardening to be added on top of that. Now, this is all done in the material description, and we discussed to start with today that the difference between material and the spatial description. So it turns out in spatial description is even better when you do with plasticity. In other words, instead of my second pure Kirchhoff stress, I now go for Kirchhoff stress. So basically, that tau is equal to F times S times F transpose. That means that if I write the principal direction of the second pure Kirchhoff stress with induced matrix C minus 1, then I can recall what S is. This is F times S F transpose. I can put here C to be F transpose F to the minus 1, and again implement F transpose. So this has to be F minus transpose. Here I multiply by F. So this equation, that equation is exactly the same when I multiply by F. And then basically I can say that this is nothing but my tau. These guys will cancel, so I have only identity. And this new I will be principal direction on my Kirchhoff stress. So this argument becomes even more, a problem becomes even simpler because this was generalized one with two tensors, not big identity, but here one of them is identity. So basically then I can obtain my spectral representation of the Kirchhoff stress by using the principal direction, tau I, happen to be the same principal directions, like for the second pure Kirchhoff stress. So it means just that when you go from one configuration to another, if you do the proper transformation, that doesn't change. And it is just related to the principal direction, which are nu I, as opposed to principal direction, which are ni. And so this is the way you can do that. I can do the same transformation for kinematic variable. So what I call the uppercase psi, kinematic strain, sort of Here is like called Z. This is the spatial representation of this one, and it's obtained as a product of F, Xi, and F transposed. So this eigenvalue problem with the principal directions, principal value Zi could be transferred to the spatial representation. So I get Z minus Zi squared times identity times nu I. And so basically with that one, I can obtain my backstress in the spatial description as alpha to be equal to F times A times I transposed. And you can get the spectral decomposition here with these eigenvectors in the spatial configuration, and the eigenvalues to be the same as the ones for the backstress in the material representation. So the fact that we are even changing from material to spatial, it does not change the principal values. That's the main point. You just change the principal direction. But this is already computation which goes into the computational kinematics. The plasticity computation is the same, whatever is the version you choose, either material or spatial. So if you take this spatial configuration, then you have to deal with the rates. For example, here you have how to compute this evolution of the elastic left Cauchy-Green deformation tensor through these corresponding rates, as opposed to doing that on the Lagrangian version of that, where you had just a GVP dot. Here you have to do it, pulling it back to the initial configuration, taking the derivative, and then pushing the result forward to the deformed configuration. And then you get this corresponding evolution equation here. You have to do the same thing for the backstrain Z that we just introduced before, which was transformation of this material description of Xi to the deformed configuration. So how you do this now computation? Well, you have certain number of variables to represent. You need to have like a global representation of your displacement field that allows you to recreate the deformed configuration by adding the nodal values of the coordinates and nodal values of this displacement to contribute to the position vector in the deformed configuration. Then you build your deformation gradient at any particular point you need it by taking the partial derivative with respect to coordinates x1, x2, and x3. And then given this current value of the deformation gradient, that means current value of the total strain, something like C, you can take the best iterative value, and then the problem reduces to computing the all the values for the position, the elastic deformation, the backstrain, and in the kinematic and isotropic hardening. Given the time step going from Tn to Tn plus 1, you want to compute the corresponding values at the next step, n plus 1, and then you recover these stresses, the Kirchhoff stress, the back stress in the spatial description, and the conjugate variable to the isotropic hardening variable Q, such that both plasticity should be verified. Well, now with plasticity, you have no constraints. You can take any value you want. And then you have to check your equilibrium equation n plus 1 to check if for this value of stresses, everything is verified. That means that it's sufficiently close to 0 with respect to the chosen tolerance. And if that not happen to be the case, you have to linearize to get elastoplastic tangent stiffness to improve the computation of the total, let's say, displacement and so on and so forth. And then you do the next step and so on and so forth. So basically here, the computation of these things is in the elastic step. What you do is as follows. You consider these internal variables are frozen. So going back to the your evolution equation, which is written in terms of rates for both B elastic, that is a left Cauchy-Green elastic deformation tensor, and this back strain in the this. So you can, when you say that these internal variables are frozen, you put this one to 0 and you put that one to 0 because this one remains no plasticity in this kind of step. So in the first elastic trial step, contrary to a small deformation setting, we simply take the values from the previous step. Here, actually, you have to do transformation, which is obtained by the current guess of the total displacement, that is the current guess on this phi. So phi transplant at iteration I would amount to making this different transformation through the let's say this velocity gradient L for this particular case. So the way you can do it goes as follows. When you're actually doing this from the time Tn to Tn plus 1, that you mean you have a different type of approximation of the deformed configuration, you can say that this expression simply preserves the viscoplastic deformation from one step to another, or one iteration to another. And you can say if I start that B of 0 is Bn is equal to Fn G viscoplastic times Fn transposed, and I have this type of evolution equation, I can introduce the relative deformation gradient, which is computed as Fn plus 1 multiplied by Fn minus 1. And then basically I can get my trial to be this, that is simply transforming G viscoplastic from step n to n plus 1 by computing it with a multiplication from left by Fn plus 1, Fn plus 1 transpose. Or I can keep it with the B elastic and use this relative transformation with the deformation gradient Fn tilde, which is equal to, as written here, Fn plus 1 times Fn minus 1. So basically, I have my trial step here, and then this will amount to changing the principal direction. So I have to recompute the new principal direction for a new n plus 1 trial, given my elastic value of this lambda n plus 1 trial. Of course, in this case, all these values simply remain the same from the previous step, but the principal directions are changing. So once I've done that, I have to, given all these trial values for the elastic stretch, for the principal value of a back strain, I can now compute my the trial value of stress. I can compute my trial value of back stress and corresponding trial value of the hardening, isotopic hardening, and I can check if my yield criteria is a negative 0, in which case the trial elastic step was just fine. If this happened to be positive, now in plasticity, I'll have to iterate to get the proper plastic multiplier. In viscoplasticity, I simply accept that, and I compute corresponding positive value of phi divided by eta multiplied by 2 to be the plastic multiplier. And then I complete the computation simply by updating this plastic part. You see, I no longer move the deformed configuration. So here you really have a split when you're having this type of evolution equation in terms of the rates. When you're doing elastic trial step, you're actually already moving the part of this, what you call it, stress rate equation, or here the strain rate equation. You take into account changing from one configuration to another by using this type of transformation with the relative deformation gradient or the total deformation gradient, whichever way you want to do it. And then you compute the new principal directions. And then once you've done it, you have your deformed configuration set, and you're simply updating corresponding measures of the plasticity, which happen to be stored in this BE and Z and Xi. So that looks pretty much like what you got in the small deformation setting. So basically, in this operator split, when you have a global computation, you have like a computation of the displacement or throughout all the nodes, which helps you to recover displacement at a particular Gauss point. That helps you to recover the deformation gradient at this particular Gauss point. And also in the elastic trial step, you have to do this transformation given this deformation gradient for each and every of these numerical integration point. And then plasticity is simply, let's say, done in the fixed deformed configuration for this iteration. And it could be cast in a pretty much the same way like we've done in the small deformation setting, which is kind of very convenient. Namely, if you want to look into it more precisely, this result, basically, I can start from the trial step. This is what the operator split does. I have done now a trial, assuming that I'm moving this through the transformation from the step n to n plus 1 iteration I. And then basically, I rely on that. And I can say that the exponential approximation to this evolution equation would give you that Bn plus 1 at the current iteration is equal to exponential minus 2 gamma n plus 1 d phi d tau I multiplied by this spectral composition ni at n plus 1 and nu I at n plus 1. So it times Bn plus 1 trial that I just computed. Similar thing is also for the back strain, where I have n plus 1 is equal to sum from I to I from 1 to 3 exponential minus 2 gamma n plus 1 d phi d alpha I and I to ni times the n plus 1 trial. And then I can make spectral composition of all these tensors. For B, I will have the final Ni, and then for the BI trial, I will have the trial values of Ni, And then I can, the same thing for Z. And basically, I can assume you can basically comparing 1 and 2 so that the final principal direction and the trial principal direction are the same, because the only transformation of the configuration geometric part takes place in this trial step. After that, I do not transform the form configuration. I'm just computing my plastic deformation and so on and so forth. So given that these guys trial and final steps are the same, I can then reduce this one to a computation of the scalar values. These are principal values. So that happens to be that BE is represented with lambda E, lambda elastic I squared, and then BE trial is represented with lambda elastic I trial value multiplied by exponential of minus 2 gamma n plus 1 d phi d tau. And Zi squared is equal to the trial value times exponential of 2 gamma n I d phi d alpha I. So here I have multiplicative update of the stretches from the trial value to the final value, and I also have multiplicative update of the principal values of the back strain from the trial value to the final value because of viscoplasticity or because of plasticity. If you want also the same thing, only gamma will be computed differently. Now, if I take a logarithmic strain, like I advocated already in this 1D version that I briefly discussed, then this is introduced as an elastic strain, would be natural logarithm of this elastic stretch. And then the trial value of the elastic strain would be a natural logarithm of this trial value of elastic stretch. The same goes for the back strain. This will like a final value, and this will be trial value for the back strain, which is natural logarithm of the Z or Z trial. And then these two multiplicative expressions, they become something that is reduced to an additive composition. Because basically you have that final value epsilon I elastic is equal to trial minus the modification. So when all is said and done, I can compute the update pretty much in the same way like I do for a small deformation setting. That is I'm computing the final value of elastic strain from the trial value, and given plastic flow, I'm computing for viscoplasticity, let's say contribution of this viscoplastic flow. Then I'm doing the same thing for the back strain, and finally for the hardening variable here. So here typically you have a set of equations to solve. You can solve it by condensing into a single equation. It all depends on all these remarks that if you have a particular choice of the yield function. And then once you have computed these final values of epsilon and kappa and xi, basically you go back and you say, given that this one was a natural logarithm, lambda that you need is exponential of that one. And basically you have this, you recover now B, E, n plus 1 in the physical configuration you have to store is basically exponential of this times the trial value, the tensor product, and Z is exponential kappa times the NI trial value, the tensor product, and you have done your computation. So you have done the full step. You have the values at n plus 1 of all the things that you've been looking for to store. And then once you converge, once you have this equation, equilibrium being verified, then you go to the next step and so on and so forth. So basically, this is the full representation how you deal with the large deformation and elastoplasticity. Some more comments on the numerical implementation. In the storage, you can have that if I drop here kinematic hardening, I have this the total strain, the axial strain, the isotropic hardening variable. I have to find these final values here, such that sigma is this and q is that. This and then such that phi has to be negative 0, gamma has to be positive 0, and phi times gamma dot to be equal to 0. So I go back here to plasticity. So really the step is that when you do this elastic trial step, you get your, let's say, corresponding update. And then you have to do the corresponding modification for the plastic part. And this type of computation are done independently for each and every Gauss points of the elements which have plastified. I will also need to compute the plastic tangent modulus. So the way it is being done, here's the linearization of your tangent computation here. So basically, I need like a second derivative of my tangent with respect to the elastic strain. And I will need the corresponding derivative of the yield function with respect to the stresses. and hardening variable and either isotropic or kinematic. So this could be worked out in the way where the unknown values are the stresses, the plastic multiplier, and the hardening variable for the isotropic hardening. And you can build these matrices in a very convenient way, and you can feed this iteration through an increment of the elastic deformation process. So what I need is elastoplastic modules with a ratio between increment of stress, increment strain. But here I have it upside down. So what I do condensation of these two equations. From this one, I can express what is delta Q. From this, I can express what is delta gamma. So I reduce it to first to kick out delta Q, then I reduce the delta gamma. That leads to something very well known in the computation. It's called Sherman-Morrison formula. This is the computing the inverse of rank 1 update of the matrix. And basically, I end up having, putting it upside down with the inverse. I get my elastoplastic modules that I put into my computation, and I can complete the computation as we go along, which is kind of handy. So this will be the illustration for that. We worked it out in a couple of papers I mentioned at the beginning that we've done both in theoretical formulation, solids and structures, and then numerical computation, computer methods, like mechanics engineering, and then after that in computers and structures for like adding these hardening phenomena and stuff. So basically, we took von Mises model large deformation setting. What it is, well, these are the principal values of the Kirchhoff stress, or like we said, is the same as principal value of second order Kirchhoff stress. They're called tau. Then I build my derivative part by computing the trace, which is the sum of these three principal values divided by 3 and subtracting these values from this value of the trace from the principal values, and I get the derivative. So you can take the derivative with respect to this derivative part, will be equal to 0, and then you basically prove that you have a plastic incompressibility. So this is compared against 2/3 of the tau y. Now tau y is your yield stress in terms of the Kirchhoff stress. And if you have plastic incompressibility, given that JP is equal to 1, and JE is very close to 1 because the elastic deformation is very small, you can safely use this to be the true Cauchy stress difference will be quite negligible for many situations in metals. If I want to extend this to more than plasticity with the perfect plasticity, which is in here, I include all kind of hardening. So I simply add on top of every tau I could get corresponding value of the back stress alpha I, which follows the same rule that I just explained, sharing the same eigenvectors and so on and so forth. So this gives me a modification of how the origin of the elastic domain is moving. And I then compare this as against not the constant value 2/3 of square root of 2/3 of tau y, but 2/3 of square root of tau y minus q, where q is a work conjugate variable to the isotropic hardening variable psi. So this can be computed in pretty much the same way like I expressed here, one after another, this type of thing. Only I'll have more of these variables. I have to include the alphas and so on and so forth. And if I take into account, let's say, contribution of viscoplasticity, it will be find the computation of my plastic multiplier. It could be as nonlinear as you want. You will have the tangent here to be changing for every iteration. Then eventually I can start and get the final values of these values and then update to a physical coordinate. So a typical choice of this would be something like that. The energy could be computed as a 1/2 bulk modulus k times the natural logarithm of the determinant of the elastic deformation tensor, all squared here, plus 1/2, 2 times nu times the ln of lambda 1 derivative squared plus ln of lambda 2 derivative squared plus ln of lambda 3 derivative. And that, if you want to add this kinematic hardening, will be 1/2 2h divided by 3 ln z1 squared ln z2 squared ln z with z a principal direction of the black strain. And then finally, you can have isotropic hardening. Could be quadratic form, could be something that represents the saturation hardening, and you can handle all this. So basically, if you have, for example, JE, simply the product of the lambda 1, lambda 2, lambda 3e, and then the derivative part is basically JE to the minus 1/3, so that the lambda 1, lambda 2, lambda 3 tilde is equal to 1. That means that you have a really like an incompressible type of behavior. And basically, you can get results that your stress tensor is recovered this way, given this result. And then basically you get the corresponding computation at the end of the VE and stuff like that. So once I've done, I can compute my stress tensor, and then I can put it into the corresponding computation of my internal force vector, tangent stiffness, and whatnot. So this becomes really the type of thing that is needed. So as I said, this has been described in a couple of these different papers. One is really like a theory formulation of the, let's say, a principal axis of the finite deformation, and then this one will be like a computational aspects when you kind of say you start with manifold, but then you unravel this, what it really means, manifold, especially in the framework of the principal direction. That simply means that once you solve your general eigenvalue problem, whether you call it manifold, whether you call it whatever you want to call it, you just deal with the scalar values. That's really a big deal about this. So it becomes quite simple. You separated the non-linearity of the problem into the large, let's say, kinematics, nonlinear kinematics, large displacement, large deformation, and so on, where this eigenvalue problem gives you this proper orientation, proper look, and then plasticity, which simply means intervening on the principal values of deformation, because like elastic stretches or back strain and stuff like that. So when all is said and done, this is actually what you get in your plasticity computation. So what I try to give you here, maybe I can, I don't know whether I should illustrate this. Where's stuff in the journals of IGSS. So, oops. So this is the one in the solids and structures, equivalent spatial material description of finite deformation as the plasticity in principal axis. So basically, it's you unable scrolling. Okay, so I listed all these things and basically listed what they are doing in different things with the scary story of manifolds and how they introduce this into the Marsden and Hughes and what's not. And then basically said, okay, you start with that, but what is the key point? You have to worry about what is the metric. So this G being on the manifold, it's not one, but it's a G. That means it's like how you compute the metric, how you measure the distance in a particular set of collinear coordinates. So once you stuck this G into that, your eigenvalue problem becomes simply a simple extension of this computation that I presented. So this is not one, but it's G minus one. And then if you do the material description of that, you see that the induced metric is further going to be C minus one. Does it come somewhere, hopefully? Yeah, here's material. And so the transformation of this metric to the initial configuration, you get C minus one. With transforming BE, you get your CP minus one. And then you get corresponding result, which is no big deal. So this is already something that you can take into account. Let me kick out this one up. And then I can also show you briefly what we were able to compute. What was that? 90 something, 99. Yeah, for the Gazdin must be this one. Okay. So we have this one. And finite deformation elasticity. Okay, and it was going from manifold to a Euclidean setting. So we start with the story of manifold. We took this formulation that I presented as solids and structures. You have to repeat the story, whatever, just the minimum. And then basically, you can say once you start the computations, you can very easily choose the corresponding coordinates and get this into the computation, which is set into the global coordinate setting. And basically, this is how you can actually deal with it. So what I wanted to show is not these equations again for the more general case when you talk about manifolds all the time. Then you can put in compatible modes to enhance the performance and so on and so forth. There's lots of things that you can hear, and then basically, then these are some different expressions. So you have a very large, let's say, a deformation of some kind of a cylinder under internal pressure. So when you have large deformation, you come to the limit, and basically after that you go into stability. Basically because you go into the like a failure instability. Then this is the Cook's membrane problem. Again, you can have large deformation. Double-edged non-specimen. What's a double-edged non-specimen? Is basically the fact that you have a bit extension. Now we recall we were doing this in small deformation setting. So when you have a large deformation setting, you can have a really sizable deformation. In particular, you can have something called necking phenomena. I don't know if the form configuration was shown here, maybe not. But we have these things in the book. So basically, the idea is like necking phenomena, you can really capture the true process of really deforming this and reducing the size of the cross section as they go along. And when you go to this one, it becomes certainly much more predictive than your usual plasticity model. So you can both deal with the let's say plasticity and a large deformation as we go along. So here, in terms of conclusion, what I've done is basically summarized here. I have introduced the type of restriction that one has to follow when building the constitutive model in the large strain, in the spirit of polyconvexity, material indifference, and isotropy. And it turned out that all of this could be followed with the principal stretches formalism. Once you pay the price and compute the argument problem, then you can keep going in the principal direction, and then it becomes very easy computation because these are scalar field, scalar type of what you call it, potential in terms of the scalar values, which are principal directions or principal elastic stretches. And then when you learn how to compute your partial derivatives, it goes very easy one after another. So basically, in the plasticity, we were able to enforce something which allowed you to have both large elastic and large plastic strain, which is a multiplicative decomposition of deformation gradient. And basically the question of strain or stress rates is completely eliminated. I don't have to worry about which kind of stress or strain rate I'm using. There were lots of developments, especially in France, of this strain rate, Yauman, or whatever, Zaremba, or Oldroyd, or Oli, or whatever it is. All of these really become the same type of story. There's really not much of a difference. And then by using this approach, I can split geometric nonlinear part and the computational plasticity. And then by using logarithmic strain measures, I recover something that looks very much like what I've done in the small deformation setting, only adapted to the principal direction. So once I have principal direction, I'm just doing the stuff that I was doing before. So that means that I can take each and every complicated plasticity model or damage model or couple damage plasticity that we've done in a small deformation setting, you can plug into this type of framework. Please recall that in all these developments, the main hypothesis is about isotropy of the elastic response. But that fits nicely into many materials of interest engineering application, for example, steel, aluminum, and stuff like that. This is fine. Even the concrete, which is kind of crazy composite material, is statistically speaking, isotropic response and stuff like that. If you have anisotropy, then you have to deal with the discrepancy between the principal direction of the strain and principal direction of the stress. Some people have done it. You have exponential type of approximation, stuff like that, but it's really never clean development because real life is never too clean. What can you do, basically? So this is the way it goes. So if I go back to some little bit thinking here, and I finished this lecture maybe faster than I wanted, but what can you do? We were quick. So the idea is like, it goes as follows. I'm recording and share screen. So I want to briefly discuss the modeling of contact. And so basically the idea is like I start with a very simple problem of 1D setting in large deformation theory we just discussed, and describe the three basic methods of contact. That is like a contact node to node. And for this very simple case, I explained the penalty method. Lagrange multiply method and augmented Lagrange multiply. You'll see that penalty method is similar to what we done in plasticity, and also Lagrange multiply is similar to what we done in plasticity. The only difference now, in plasticity, you talk about local constraint, about admissibility of the stress field, whereas here you talk about global constraint, which concerns the boundary, which can be the contact. So in this case, it's easy because it's a bar entering into a single point into contact. So explaining these three methods is very simple. But in 2D and 3D case, it becomes a little bit tricky because you have to define what is called the proper description of the contact. And so the first work was the slide line algorithm. That means that the two bodies can meet and then start sliding on top of each other. And then turned out that this was very tricky business. And people took a lot of time before this understanding how you can represent this, either by smoothing this surface area. So there was, the first approach was a simple contact element with one node of the slave body and two nodes on the master body. Paper by Riggers and Simo spelled out that one. And then they had like a smoothing this surface with the Hermite type of polynomials that was work over heterogeneous Barth. And then you also had the motor elements and things like this. So here's the stuff that we are considering. We are basically taking into account the contact node to node, and we have a problem with any sketch on that one here. I have an initial configuration here, which is the length L, and I take a loading which brings me into very large deformation. But this time around, this large deformation is not possible because a certain distance, G0, this initial gap, you place a rigid obstacle which doesn't let this structure go forward. So basically here you have to define the usual boundary condition on the left-hand side. And to start with, you have to define the boundary condition on the right-hand side that you're applying the force. But if you also put the initial gap, you have to take into account at a certain point, this boundary condition, what is the force doesn't really matter, because what takes over is the fact that you cannot go beyond this distance here. So you have to define initial gap, and for each and every time step as you go along with the current value of the deformed configuration LT, you have to define the current gap. And so basically you make sure that this GT, the current gap, at the end when you come into contact with a rigid obstacle, has to be equal to 0. That means you cannot go forward. And then traction you apply doesn't really matter. What really matters is this pressure that comes from the rigid obstacle, which is really not letting the structure advance, even if you keep applying the loading. So these are type of things that we want to study in this case. So now the condition that you have to respect, that this gap in time has to be, the way we defined it, to be difference between the current position, the length and the current position x bar. Basically, it's a negative. So your G is either negative or 0 when you come in contact with the rigid obstacle. Your pressure is either positive or 0. And then the product of these two is equal to 0. That means like either the pressure is 0 and gap is negative. That means you never reach the contact. Or the pressure is positive and the gap is 0. That means you are now in contact. These are the non-penetration conditions spelled out by Signorini in one of these books written in the Handbook of Physics that Truesdell was kind of commissioned to many other people. And they're equivalent to the contact condition that we done in elastoplasticity. The only difference is now that this is not done at each Gauss point. This is done globally over the boundary where the contact can happen. And normally you don't really know this boundary unless you're in a very simple situation like this one, where obviously this boundary is right end of the bar and nothing else could be there. So really this is by far the simple situation. How do we actually define the behavior for such a case? Well, this case is so-called non-smooth, non-differentiable type of thing, and you cannot obtain the boundary, you cannot obtain the constitutive behavior for a contact to be something like P at any time T to be some kind of function, P hat of G, the gap at any time T. Then you go into something called the convex structure computation. You introduce notion of subgradient. This was done by Moreau, which was a professor in engineering in Montpellier. And then basically they're saying that this was their best mathematician. And then a mathematician, Temam, who was a former student of Jacques-Louis Lyons, he wrote also a book on this one with his collaborator. And in US, you had Oden, who did the same thing. So basically, you can say that the constitutive behavior for the contact is equal to this subdifferential of this, and this subdifferential is defined by so-called indicator function, which has 0 value when G is negative, and it has a positive value when G is positive. So indicator function becomes something like basically that you have to spell out in the convex analysis that says that I can compute P such that the product between P and GT for any type of T minus G, the real one has to be positive. In other words, if you want to think about that, is this indicator function. Let me just draw it quickly. This indicator function is something like this. This will your let me put something like this indicator function and your pressure. So it's basically this one here and that one there. So basically either you're on this side or you're on that side. And then basically the problem becomes when you reach this value which is equal to 0. So first idea, instead of this guy, I can actually penalize, and I can do something which is augmenting this with the corresponding value of G, having an extra term, so I can compute my pressure really by having a unique expression and smooth one, so that the computation goes along without any difficulty. So this is kind of a penalty term. So here's a penalty term. I add basically 1/2 GT squared, and I put a K. What is K? Well, here you have some rigid obstacle, but you can imagine replacing this obstacle by some kind of very stiff spring, K. And then basically we have this situation where you reach the contact with the spring, and then spring and the bar together are resisting the increase of the loading. So basically that after that, you can indeed compute the pressure by basically taking into account the derivative of this guy becomes Macaulay bracket of G, the gap, multiplied by K. And so K is really the stiffness of your spring that is replacing the rigid obstacle. So basically this is one way of doing it, but then I no longer have really non-penetration condition, because basically there is a value of G which is positive, which is not admissible before, but now it becomes admissible, so you can go into the obstacle and then compute whatever you can do with this one. So basically the idea, this was done, and it is done in many software applications like Dyna3D, which was done for testing the efficiency of nuclear weapon explosion and stuff like that. And the idea is that it's much easier to deal with the contact problem when you have a penalty formulation, because you can compute the pressure as you go along from the given deformed configuration. Of course, what you don't get perfectly, you don't get this constraint on non-penetration. And then you can have, if you've poorly chosen your K, the stiffness of the spring, which is resisting penetration, then you can have a very large penetration. So people initially use the computation of the 3D model to get what you call it, the crash test and stuff. And you can see car entering for whatever couple decimeters inside the wall, which is certainly not realistic. You wonder how come the results any reliable. So if you want to do better, then you can take a Lagrange multiplier approach, and even better to take augmented Lagrange approach. So it's always a subtle game between taking a value of K which is big enough to get a reliable contact, or small enough which is giving you the nice computation. What is the problem? When you have this one, basically when you're having a penalty function on top of your stuff that you put there, you have an extra term which is entering your stiffness equation in the n degree of freedom, which is on the right-hand side. You have this K. So if K is much bigger than the rest of the structure, then it gets dominated. So you get a very, very large eigenvalue, and then you have a so-called stiff system of equation, which is hard to solve. So if you now want to do better, you can put constraint on top of your equation equilibrium. Basically, you introduce the Lagrange multiplier on top of this gap, and the Lagrange multiplier is nothing but the pressure, such that the product between the pressure and the gap is equal to 0. So you really get into this constraint principle is now reduced to unconstrained principle for any value of phi. and P, the value of pressure, which is positive 0. So now you have it extended system with the unknowns to be D, the total displacement vector, and P, and you can solve this in a better way. And in fact, the last equation becomes simply the imposing that the gap is equal to 0. So everything seems to be much better, except that you have a changing profile. Sometimes when you have a contact, there's a G to be equal 0, and there's positive value of P, but then you don't have a contact in next iteration. So you don't have any P, and this equation should be removed. So this switching from one state to another, it leads really to a fragility of your computation. And even though it's theoretically better, practically it's no big deal. I mean, it's really not easy. There's something called duality. If you want to show there what will be the best update and so on and so forth, you can go through this and you have it in the book to talk about that. But in any case, duality would mean that you have this to be negative, and then this one P becomes like a maximum value and stuff like that. Let me not dwell on that. So now, if you want to get exact penalization, that will be, of course, possible, but you need this indicator function. Again, this is not quite fine, so it's replaced with this one. And again, the problem here, you have like a ill condition of your stiffness matrix if you take a very large stiffness and if you don't. So what people are doing, of course, this is exactly the situation, because you have extra term, which is of this stiffness of your obstacle, and then becomes dominant part of your stiffness matrix, and you get really very poor condition of your equation. So what people finally did is the following, called augmented Lagrangian formulation, which, by the way, you could do also using for plasticity and many other things. So you actually choose the stiffness which is good enough for this obstacle, so that you're actually having a good conditioning of your tangent stiffness. So this is K0, not the real one that would really be required. And then you, this is so-called penalized, and then you also dualize. That means you go to the Lagrange multiplier method. When on top of that, you put on top of this one on the top, you put this one extra term. And then when you reach the value when G is equal to 0, this penalty term will drop anyway, and you get the proper value of P. So the advantage of this formulation, you always have some contribution of the gap. You don't worry whether you're changing profile, you never change the profile. And then P could be the 0 or positive. Again, you know how to adapt to that. This is so-called augmented Lagrangian procedure. So here, what is it? You are minimizing the strain energy function, the one with the penalization, and the one which is dualized. And you're computing the proper value of phi given the iterative value of the pressure. The update of pressure should be really done with the real kind of a duality statement. That means with the full tangent stiffness and K0 times the rank 1 update is for the last node. But what the hell, it's too complicated. Often people just replace it with K0 and they do this linear update when you do computation. And so basically in the process, you can recover the computation of your stuff. So you can do this with the inequality constraint by introducing this trick where you introduce Z to be equal to defined this way. And then you can actually get augmented Lagrangian in this format, where you kind of compute the let's say the current value of pressure, and then you minimize and so on and so forth. So this is the kind of thing that is then the best way in terms of computing, because you have both the choice of K0, which is giving you the right conditioning of your stiffness, and also the current value of your let's say the pressure, which is like a multiplier type of thing. Then if you go to 2D, 3D, let me just briefly discuss, because we are coming there. I don't know how many of you have this as a problem. What I could see, what you describe, what you're doing, not many, but the idea is like the big deal is really hard to describe the contact. In other words, when you have two bodies in contact and they are represented by jagged edges, so let me skip all this. Basically, the idea, what is the illustration? I'm looking for the illustration, sorry about that. Hopefully it will come, it has to be somewhere. No. The idea is that it's actually a very small chapter, it's only 20-something pages. I don't have it here, do I have it there? Okay, neither that. Okay, doesn't matter. So basically, I can do it in with the sketch. When you have like two bodies in contact, you know, here's a body one and body two. So basically, you have to decide how to discretize this. So it comes down to some kind of certain number of elements, and so it's not really these smooth surfaces which are in contact, but something which is not. And then typical thing is like you describe one to be a master and the other one to be a slave, and then master will give you what is the direction to which you are checking the contact. So you define the normal to the contact, and then you define all the nodes that can come into the contact by doing this motion here or there and stuff like that. And then you take the distance between this slave node and the two master nodes. So the simplest element is the two master node giving rotation of n and one slave node. And then you build it from there. Or you can do the smoothing. You can do Hermite polynomials and smoothen this out. Or the final thing, which is the best, you can do something which is mortar methods. So mortar is like putting a layer of mortar between two bricks. And basically this way you actually reduce it to connecting this to you then discretize this intermediate surface. And so you have a contribution from this and a calculation from that. Because the problem is we have a slave master approach. If you take one body as a master and the slave, you might have a biased results, and you don't really have the proper computation unless you then change the roles. So you have a two-pass algorithm. Where once is one slave, the other times the other one slave, and then you recompute and you average. So in the mortar, this is done automatically, and you basically then integrate all this and so on and so forth. So really, conceptually, the contact problem does not introduce too much of a new, let's say, theoretical difficulties. I described these three methods which allow you to understand this, but the practical thing is really about meshing and finding the contact domain, or you have a self-contact and things like that. So there's typically lots of coding. I actually was in a situation where I worked with I was in collaboration very close with the two guys who did their thesis in the contact mechanics. One was working in Germany with Peter Rigas. The other was working with Roger Owen in Swansea in UK. And both of these groups were really leading groups in contact. So at a certain point when we finished the work, we went to the coffee shop, or not to say drinking shop after midnight. And then basically you keep working, and around midnight you say, okay, what the hell you work with? What do you use for contact yourself? I say, what the hell you two guys are the best experts on that? You're asking me, what do I do for contact? Well, I say, because it's not working all the time. So the problem is that it's not formulation, but the big sensitivity of this model and the kind not working all the time. So one has to do regularization and thing of this kind and so on and so forth. So let me maybe